we good now? Are we good now?
Are we?
Oh my god.
Yeah.
Do we have video and audio, everything? Okay.
Maybe.
Sorry about that. Yeah, okay, good. Sorry about that. Oh my god. Okay. Hello, everyone. Aki-nyan here. Sorry for the technical troubles. My audio was working fine right up until OBS apparently, and then OBS just decided that it was not going to connect. I'm so sorry. Hello. So today I have with me a very special guest. Aki-nyan from nullptr Live. Say hi.
Hi.
I think, actually, you want to check your, noise reduction stuff? Because I think it might be a little bit too aggressive.
Is that better?
I think so, yeah.
Maybe.
Hey, cool.
I have perpetual Discord audio problems.
Discord always does that. Alright, cool. I think okay. Audio problem solved. It's always scuffed like this, right? With collapse.
Yep. Hi.
Alright. So today we're gonna talk about chip design. Wait, so what's this about? Can you tell us a little bit about it?
Yeah, so I was hopefully gonna go over kind of like the beginning of chip design. So, little TTL here, some CMOS there, and then kind of get into a little bit briefly of the history of VLSI, or very large scale integrations. And then we can wiggle on and get our hands dirty and actually designing an inverter and then a buffer if you want to go even further, and then we can maybe even spice it.
I have no idea what half of this thing is about. I've heard some of these words maybe. All right, let me say hi to everyone, and then let me say hi to everyone, then we'll get right to, because we actually have a lot of chat. We have 120 people and we haven't even started yet, which is crazy. So let me say hi to everyone, and we'll get right to it. Alright, hello, Leave W Brush, hello, Trismix, hello, Asa, hello, Alexander Bornish, hello, Cubic, hello, DP, hello, Christopher Jackson, hello, Analytic Mind, hello, Aki-nyan, hello, Wolfboy, hello, Linux Dude, hello, Kerbo, hello, Naseb, hello, who's next here? Luna, hey Luna, nice to see you here. Hello, hello, I think I already said Wolfboy, hello, Bob 10, hello, Noah Williams, hello, Root, hello, Dadang, hello, Ciani Boy, hello, Novia Riptide, hello, UA 99, hello, Cardiac Seed, hello, username not available, hello, I think that's everyone there, Marco, hello, Neji Cookie-san, hiya, hello, Aura, hello, who's next to that, One-Q, hello, mostly the same people. Fiverr, hello Fiverr. And is that everyone? Hello FJV. Lots of chat before we even started. Okay, I think I didn't forget anyone. Hello Jose Lopez. Hello Florent Castelli. I think that's everyone. Hello everyone. Setman, I think also. Okay. And Coconut Man. Oh, we have a lot of people. A lot of new people also. So that's really cool. Every archive, I think I also missed. Hello, Alien. Hello, everyone. Hello. Any Verilog enjoyers in the chat? I don't know. New people, yes. So yeah, what are we gonna do? Can you give us a little bit of overview before we jump right into the getting our hands dirty part?
Yeah, so for those who may not know, CMOS is one of the more modern as in coming from the 80s and 90s.
What does that stand for?
Modern. So CMOS is complementary metal oxide semiconductor. To a point, I can't explain too much because we start getting into more material engineering and physics, and to a point, quantum mechanics. But essentially, it's taking advantage of the fact that silicon is a semiconductor, and you can dope it with boron or phosphorus to change its relative conductivity. And using those, you can then make the electrons wiggle.
So why is it called complementary metal oxide semiconductor?
Yeah, okay, so it's called complementary because the two prior technologies were either just plain PMOS, which is for P-type semiconductor material, and also P-MOSFETs. It's a special ratio of how the transistor is designed. And then there was also NMOS, which is sort of the antithesis technology to that. It deals with n-doped silicon and works basically the opposite way that PMOS does. So what CMOS is a combination of those two technologies to form a more stable and lower power target, basically.
So it's complementary because it's using P and N at the same time, right?
Yeah. So it uses both N MOSFETs and P MOSFETs to form logic gates. So it's complementary. And because the PMOS is generally used for pulling signals up towards supply voltage, and NMOS is usually pulling signals down towards ground, typically, but it doesn't have to be ground, right? So they're complementary because you're pulling the signal in either direction.
Okay, so it's when you have PMOS, you're pulling up. When you have NMOS, you're pulling down. And when you have CMOS, it means you can do both alternately,
Yes,
right?
Essentially.
Okay.
This isn't getting into like past transistor logic and all the absolutely cursed stuff, but as a simple explanation, yeah.
Okay, so we have like voltage on one side and ground on the other side, and you want to send that somewhere. And so if you want to send a positive voltage somewhere, you would use a PMOS transistor, right?
Yep, essentially.
And then if you want to send ground somewhere, you use an NMOS transistor. And if you have both, you can send either of them to the other side, and that makes it faster, I guess.
It makes it so the current leakage is less, essentially. Because there's also a state where neither of the transistors are active. We call that high Z, or high impedance, and that means it's just floating there. So there's no current transit through the MOSFETs. So it essentially uses zero power.
So what's the MOS part? Oh, sorry, go ahead.
So the metal oxide semiconductor. It's because we use stacks of silicon dioxide and polysilicon to build these.
So there's metal oxide semiconductor, but like, what's the how does that look physically? Like, is there?
I don't have anything to sketch it with you, but to put it very simply, so let's say we have a ground plane, which is just Wikipedia actually has a very good diagram of this.
Let me see if I can find it, maybe.
If you just look up an NFET or a PFET, MOSFETs, that would probably have a good description.
Okay, let's switch to the screen.
Yeah, there we go. That one's great.
Okay, let's get the screen on. There we go.
Yeah.
So this one, right?
Yeah, so that would be a NFET, yeah. So your silicon wafer is P-doped, and that's what they're calling the P substrate. And then you have an N-well, so the N-well kind of expands around where the two N plus contacts are. That is N-doped silicon, so it has phosphorus atoms implanted in it to give it extra electrons.
Okay.
No, it has phosphorus atoms implanted in it to give it electron holes. Sorry, this is where we're getting into like the chemistry stuff.
I think it's if we can just like simplify and say sort of how the current flows and what controls it, and the positive and negative and stuff.
So a MOSFET has three parts. You have the gate, the source, the drain, and then optionally, and it's illustrated here, you have the bulk connection. So the gate is what controls the flow of electrons between the source and the drain. So to turn a MOSFET on, the gate voltage has to be slightly higher than the required threshold. But what that does is it pulls electrons in from the bottom to create a path between the two end wells, which then creates a essentially electron tunnel, which then lets current flow.
Interesting.
Yeah, sorry. I'm not good at explaining this.
No. Someone asked, why is it called doping exactly?
Because what it's doing is it's taking a pure monocrystalline silicon wafer, which is something ridiculous like 99.99999% pure, and then we're adding impurities to it. So you're essentially doping it one direction or another to create a surplus or a deficit of electrons, because silicon is a very stable atom. And doing that is what we call doping.
So you're basically adding impurities, and that's why you add extra stuff, right?
Yeah, you're adding impurities into the silicon.
But the substrate here is actually, it says P substrate, so it's already doped?
It can be, but there's a few steps in the manufacturing process where essentially there are pre-doped regions where you define transistors. At least as far as I'm aware, this is getting into kind of the nitty-gritty details that people don't like talking about because multi-billion-dollar foundries are on these processes.
Kind of, this is how we make gold usable. We have to add impurities to make gold useful for things like copper, right? With gold. Yeah, it's kind of like that. Yeah, so my understanding is the silicon is actually basically an insulator on its own. It's a semiconductor, but that's more in relation to other things you do to it, right?
Yes, but there's also silicon dioxide, which is a very excellent insulator.
Yes.
Which is also used.
I guess this is convenient to just like oxidize the silicon, right?
Yeah.
And silicon dioxide is glass, right?
Yeah, they're called glass passivation layers. That you basically grow glass on top of your microchip.
That's pretty cool.
Yeah.
So we have the P substrate, which I guess is silicon with extra stuff added to it as a baseline. And then we have you said this is the N well, this dark red thing.
Yeah, that is where we add N-type silicon or atoms to make it N-type silicon.
But then there's these N plus sections, right? So
yeah, those are higher diffusion areas. They essentially they increase the N-ness.
Now I'm getting lost.
Yeah, I'm kind of lost. I'm not into the deep physics of this stuff. So we're approaching the edge of my knowledge here. As far as I was aware, it's just a stronger doped region.
Okay. So let's talk about this part here, the gate, right? So what's with the colors here, the yellow and the red?
Okay, so the gate is showing the layer of polysilicon and the layer of silicon dioxide. So the orange is the insulator, it's the silicon dioxide, and then the red above that is the polysilicon. And that's what actually forms the gate of the transistor. So you put electrons into the polysilicon, which then pulls electrons from the P substrate up through into the N diffusion, which then lets the electrons flow.
So wait, it's called a metal oxide semiconductor, but where's the metal?
Silicon is a metal.
Oh, okay.
Yeah.
Okay.
And then we also use things like aluminum and tungsten and all that kind of stuff in here. But the metal oxide is the silicon dioxide.
Oh wait, is it metal oxide semiconductor or metal oxide semiconductor?
Yes. I don't actually know if there's a distinction between that. That's a very good question.
Let's find out. Let's see what Wikipedia says.
Yeah, that's a good
metal
question.
insulator semiconductor.
Metal oxide semiconductor field effect transistor.
Metal.
So I guess it is metal oxide.
It says the metal in the name MOSFET is sometimes a misnomer because the gate material can be a layer of polysilicon. Okay, so this is one of those things where someone came up with the name and the name is kind of wrong and we keep using it because everyone's used to it.
Yeah, that's this field has been around longer than computers, so.
Okay. So then it's three things, right? We have the metal, which is not a metal because engineering terms are cursed, and
Yes.
and then we have the oxide, which is that silicon dioxide or whatever.
Mm-hmm.
And then we have the semiconductor, which is the silicon, right? The stuff at the bottom. So that's why it's called MOS, right? That's the N, that's the O, that's the S.
Yeah. And then this would be an NFET or an NMOSFET. So the drain would be towards your positive voltage rail and the source would be your ground.
Mm-hmm. It's interesting. It's kind of symmetrical, right? You have like the source and the drain, but they kind of look the same.
Yeah. They're essentially the same. When we're drawing out an inverter, the structure will be made a little more clearly, I think.
Mm-hmm.
But yeah, they're essentially symmetrical if you ignore the body connection. from
Right,
the
this thing at the
transistor.
left, right?
Yeah, that for all intents and purposes, it's connected to the source, but it doesn't technically have to be, but it really should be. And that's where we're getting into, confusing.
Mm-hmm. So wait, when we
First
say
stuff.
source and drain, what do those mean? What's
That's a good question. Because when you're building with NFETs, the drains are all pointed towards positive voltage. So I guess it depends on how you look at if your electrons migrate from positive to negative, or if electrons holes migrate from negative to positive.
wait, but electrons migrate from negative to positive, right? Because electrons are negative.
If you subscribe to electron theory, then there's electron hole theory, which has everything reversed.
Okay, but like holes are plus to minus, and electrons are minus to plus, right?
Yeah. Well, no. Yes.
I
Yes.
thought
Yes.
so.
I am so
confused
sorry.
now.
I'm confused too. I have confused myself. But yeah, essentially, the electrons are, quote unquote, migrating from the source through the NFET to the drain until they get to a PMOS, in which case they're going up through the drain, out the source.
Interesting. Okay.
Yeah, current flow and electron flow are different. This is where we're getting into the physics.
I mean, I don't know. In high school, they said that electrons are negatively charged, and in a battery go from minus to plus.
Yeah,
That's all I know.
That's a very simplistic way of viewing it, but once you get down to this level where everything just barely works. So
Weird. It's been 20 minutes since the stream and we're bloody cursed.
I apologize. I apologize for that.
I don't think you need to apologize. I think this cursed silicon is just cursed.
Yeah, let's move on to VLSI.
Okay. So what about VLSI? Should I look up a page or something?
You can, but I can explain it.
Okay.
So back in the day when they used to design integrated circuits, they would do something called cutting it out of a giant piece of film. So it's called rubylith. And what they would do is they essentially put this giant sheet of rubylith, which is like a plastic polymer material, on a light table, and they would physically cut the gates out.
That, I guess.
Yeah, that the picture of the person hunched over the drafting table was really good. So that's what they used to do. You used to sketch it on paper, and then you'd cut it out at a drafting table, and you drew all the gates like this.
I don't know if I
And
can
then
zoom
this
into this
would
one.
be, yeah, but it would be projected, and then it would be scaled down, and that's your chip design. So yeah, you'd cut all the gates out like that, hunched over a light table for who knows how many days.
That sounds really
And you had-
cursed.
Yeah, and you had to do each layer like this.
And this is like a
So-
repeating pattern or something they're doing there, right? Like it's not even.
Yeah. I'm not entirely sure what that is. It could be SRAM?
I don't know. I have
SRAM
no
wasn't
idea.
around back then. Yeah, I don't know exactly what that is, but that's essentially what they were doing. And you had to do that for each layer. And this was very slow, as you can imagine, and error prone. And then as designs shrank, so once we got into the single digit micron range, which is insanely small, and there's a lot of detail. So the chips are getting bigger, the details are getting smaller. This is not entirely feasible to do by hand. And then, so two hardware engineers realized this. I forget their first names, Mead and Conway. They essentially pioneered this thing. It's called Mead-Conway VLSI chip design.
Wikipedia should know. Wikipedia should know. Here, Carver Mead and Lynn Conway.
Yeah, Lynn Conway and Carver Mead. They essentially devised this thing, and it was partially funded by the DARPA VLSI project, where you would design standard cells, like little blocks of logic, and then you'd be able to use these blocks of logic like Legos to form larger structures, fairly automatedly too. So this is where you take, at this point, take something like Verilog or VHDL, stuff it into a computer, and it would spit out the gates. And that's how you would do it for these monstrously large chips, right? So.
Hey, Trevor, thank you so much for the super sticker. Thank you so much.
Yeah. So these two people did great things when it comes to semiconductor design. But the big thing was using standard cells, right? So
you basically
means
like make like a bunch of Legos or something like that, right? And like build them,
you
build up.
essentially make the Legos and then put the Legos together.
That's really
That's
cool.
simplified. Yeah, a simplified way of doing it. But you still have to design the Legos, right? So VLSI layout is still a thing that is actively done because all of the foundries, as they're called, design things called PDKs or process design kits. And those are the Legos or the little blueprints for the cells that are put together.
I like how we have the system on chip C also, and then the M1 is literally the first picture.
It's fortuitous.
Excellent.
Ow. Sorry, Annie is biting me. I don't know.
Annie! Annie's always up to her
Cat wants-
shenanigans.
Yeah, Annie wants her 5 minutes of fame too. She wants tummy time. That's what she wants. Yeah, so the foundries develop these PDKs, Annie, which are essentially their secret sauce to standard cells in how their essentially factory produces silicon wafers. So then we get these PDKs and they're manually designed cells, and then automated tools lay them out based on synthesized Verilog code, essentially.
Someone says, is it kind of like Factorio blueprints? I don't know Factorio. Do you know Factorio? Yeah? Okay.
Yeah, it's kind of like Factorio blueprints.
Nice. So... So then once you have those standard cells, like, okay, so the founders have the PDKs, but then can you also, like, make your own cells? Or how does it work?
So, it's split up between digital and analog design. Analog design is a lot of laying out the gates and the silicon and the polysilicon and all of that stuff yourself. And that's how these really high-speed designs are done.
Mm-hmm.
So things like PLLs or oscillators, they're traditionally done in the analog domain.
PLLs?
Phase-locked loop. So it essentially does some really fancy signal math to try to match a voltage-controlled oscillator, which causes wiggles very quickly, to a target frequency. It's essentially just an example of analog design,
Okay, but
right?
so that basically a clock generator, right, or something like that.
Yeah, it's basically a clock generator. It still needs an external oscillator to be fed into, but yeah. And that would be analog design. So you have to lay out the internals, like the charge pumps and all of the cursed analog magic that goes into those manually. But then you have essentially, and they're called IP blocks, intellectual property blocks, and this is a big thing in FPGA land too. But it's essentially a layout, so it's its own layout file, just like the standard cells are, and you can just drop those in your design like Legos too.
Okay, so it's just like buy like a pre-made circuit and use it, right?
Yeah. You can do that. There's a few companies that do that. ARM, as you know, you can buy designs from them.
Yes.
And then the two big ones for sort of in the ASIC space, application-specific integrated circuits, is Cadence. They're the big ones. They make the big, expensive Virtuoso layout suite, which is sort of the industry standard. If you go to university for learning this, your university would likely have a license for it. If you're Apple, you're probably using it. And it's this monstrous Linux application that you have to export over from a remote server. And then you also have to deal with SSH forwarding for PDKs because you're under an NDA from TSMC and all that stuff. But it's like this multi-million-dollar piece of software. But they also sell IP blocks and pre-made silicon
scary.
layouts. Oh yeah, it's terrifying. It also looks straight out of the 90s. And then there's Synopsys, and they kind of do the same stuff. They're a little less well known in the ASIC space, but they mainly sell IP blocks as well. I'm not entirely sure how big they are into actual silicon IP blocks, but
I think Apple uses some Synopsys stuff, like the USB.
They probably do.
Controllers
I
are
think they're really
Synopsys.
yeah, I think they're big in the memory and PCIe IP space.
Yeah, I think the PCIe is also Synopsys.
Yeah, probably. And then there's Mentor Graphics, which was bought by Siemens, and they were big in the ASIC validation space too. But there's a bunch of these, there's only like 3 or 4 companies that really are multi-billion-dollar giants in this world. But you essentially buy pre-validated Legos and tools from them. In the open source world, there hasn't really been a lot in the world. But DARPA was actually trying to change that. So DARPA had this initiative which spawned something called the Open Road Project. And what they did is they collected a bunch of tools that were floating around and built their own to make a fully open source tool chain that allows everyday people like you and me to actually design and produce ASIC plans.
That's really cool. Is there a page I can show about while we talk about this?
Open Road, I think.
Open what? Open
Road?
Road?
Road, yeah, like vroom vroom.
I think
do Open Road DARPA.
Open Road?
Road.
Open Road.
Yeah, Road.
Open Road DARPA. Oh, this one.
Yeah, there it is, the Open Road Project. So, yeah, they're doing a bunch of stuff. So now we have the software tools, and as the main issue is getting your actual microchip fabricated is very expensive.
Right.
There's
So,
like minimum order quantities.
How expensive are we talking about?
Anywhere. So if we're going like full production run, anywhere from $800,000 plus, averaging in the millions.
I don't have that kind of money.
Yeah. But Google, being the benevolent overlords they are, partnered with a few other large companies, and they are doing something called an MPW, or a multi-project wafer. So you have a bunch of users that built their own ASICs, and then you put them all on a single wafer. So they're doing this primarily with Skywater. So if you search for Google MPW will bring it up. They partnered with eFabless. Yeah.
Wow.
I think this one. Yeah. So Google's doing this for obvious personal gain, because if they're letting a bunch of people who like to do open source hardware and software, they're going to want to improve the tools,
Right,
which means
right.
Google doesn't have to pay for cadence.
Right.
And that's their main goal behind this primarily. But it allows everyday people to actually test the tools and their designs on wafers.
So
I don't think
can...
MPWs ended after 8, Hannah. Sorry.
On the chat, yeah.
Yeah, so they partnered with Skywater Foundries, which is a foundry in the United States.
Mm-hmm.
And they open sourced their 130 nanometer PDK. So we got all the standard cells and the simulation data and the characterization for the Skywater process. And then combined with eFabless and Google, we can now fabricate or submit designs for fabrication.
I already see cat girls.
Yeah!
Are people
really
already
cool.
putting cat girls into chips?
Yeah, that one's really cool too, because that one specifically, I believe, has a 5 gigabit per second transceiver.
It's literally a
analog
Git
design on it.
project. Wait, but the image isn't showing. Why isn't the image showing?
Yeah, I don't know, but
Important. What?
yeah, same mood. Chip design is complicated.
I have no idea what I'm doing. I just saw cat girls and then I couldn't see cat girls anymore.
Yeah, it's a shame, but yeah.
That's
so
really cool, though.
People are submitting designs, and it's not necessarily transistor art. It's you can create metal layers to synthesize art.
Mm-hmm.
But there's a lot of stuff here. People have done custom FPGAs. They've done custom analog designs. There's been 150 million RISC-V processor submissions. There's been SRAM tests. I believe they submitted a full 64-bit microwatt power
Wow.
PC core.
That's crazy.
But yeah, so, and these are all open submissions. So using the tools, we too can design something, have it submitted, and have it be fabricated.
So how that you literally just do it and send it to them and they make it, and it's
Essentially, there's a bunch of rules. There's design rules, and you have to make sure that your design is actually manufacturable and won't absolutely trash the entire wafer because
Right.
you're sharing the silicon space. But yeah, so we can submit designs. And then eFabless does another thing. They do, it's called Chip Ignite. And it's not a free MPW, but it's an MPW service, and it's a lot less. It's about 10 grand.
Oh,
And you
okay.
get like 100 chips out of it. Yeah, $9,750 per project. And you get
That's more.
like 100.
Yeah, that's more affordable.
It's about, I think it averages out at like $97 a chip, which is still
it's cheaper than a
expensive,
Mac
but
Pro.
we're not, yeah, but we're not talking millions of units, right? So research and academia tend to use these multi-project shuttles.
That's really cool though that you can actually like get a chip made for, I guess for free with the Skywater
so,
stuff, or for something that you could actually afford,
Yeah.
especially like as a small company or something, right?
Yeah, it's geared towards the
Hey,
small
and someone
companies,
says
startup
affordable.
kind of
Okay, when the baseline is like $1 million, right? $10,000 is affordable.
Comparatively, this is immensely affordable. There's a few other MPWs out there. I think there's one that targets TSMC node. It's sub-micron. I think it's around 15K, which is still expensive, but it's a lot cheaper than trying to buy a full production line of wafers, right?
Someone asked, Galaxy says, would you get bare silicon then? You still need to package it?
They give you packaged silicon. I think you have an option of like it's 100 QFPs or QFNs or something like a larger amount of WCLSPs, which are essentially bare dies that they slice up and put little solder balls on the bottom of.
These are chip packages, right? Like QFPs and what are you saying?
Yeah, these are different ways of packaging chips.
Okay.
Sorry, cat's also distracting. So that's kind of the ecosystem. So there's a bunch of open source tools that let us do these designs. And we have the PDK stuff too. So hopefully today we'll be able to get you to build your very first Sky 130 CMOS inverter.
So
all with open source tooling.
How do we get started? I hope we can compile everything for ARM because I'm doing this on ARM. So
yeah, so there's a few things we need first. We'll need the tools themselves and also the PDK. The PDK might be the least painful thing to actually get set up.
Okay, let me make a directory and we're gonna start. What should I call this? Chip design via chip design, I guess.
Yeah, if you want. I have a special section just called ASIC under my data pool.
Right.
And then in here, the PDK and everything will live.
Okay, we'll just put it in here. So.
Okay.
Okay, what?
So do you want to start with the PDK or?
Whatever you think makes sense.
All right, so you have Python in this machine, right?
Yes, I have Python 3.12, I think.
Oh, yeah, that's perfect then. There's a Python tool called Volare, which is used for managing the open source PDKs.
Volare? Can you spell that out?
Volare, I believe.
This one? Oh, it's in PyPy, okay.
Yeah, it's in PyPy.
Okay,
so you can just install it. I installed it in a virtual environment.
Should I use a virtual environment for everything, or does it matter?
That doesn't particularly matter. You only occasionally invoke Volare, so just having it as a separate virtual environment is fine.
Okay, we'll just do it in my home thing and hopefully nothing breaks. Yeah. Okay, we got that.
Okay. So
I think it's not in my path. But I do have it there, okay.
Yeah. Hearth.
I should actually let me add that to my environment because I do actually want that. Okay.
So Volare does two things. It does PDK management, and it can also build the PDKs for you in case there's a library or cell library that you don't have. So if you just run Volare, it'll show you all the actions it can do.
Okay.
So what we would want is ls remote. Oh, wait, before we do that, sorry. Where do you want your PDKs to be placed? I
want everything here under chip design. I don't know what structure you would want under that.
So we can make a directory called PDK.
Okay.
And then we want the environment variable PDK root, so PDK underscore root, to be that path.
Okay.
Yep. So this is where Volare will install the PDKs, and then this is also where all the tools will look for the PDKs that are installed.
Might as well also let me... Let me put this into my environment so it stays forever. I think we're fine then. Yeah, that should be fine. Okay.
Yep. Okay, so now when you invoke Volare and then ls remote, it'll list all of the pre-built PDKs that exist.
What? I see a lot of good hashes.
Yeah. So the most recent one is fine. So you want to make sure you copy that hash. And then I think it was Volare enable and then that hash. And what this will do is download all of the pre-built cell libraries.
I think I'm cropping the left a bit. That's better.
Yeah. So this will take a second, but it will be a lot faster than actually trying to build them from source. And we don't have the tools needed to actually build the PDKs from source.
When we say build the PDK from source, what does that mean? Because I assume you're not using GCC and C files and object files. So what does compiling mean in this case?
So it's not necessarily compiling. You can kind of think of it that way. So all of the cells, the standard cells, are independent files.
Okay.
Right? So you design an AND gate, and you design an OR gate, and you design a NOT gate. And then all of these will be classified and characterized. So you do extensive SPICE simulation, and you may even fabricate these and do environmental measurements. And then all of this data is per cell, per fabrication likelihood. So there's a few things called fast, slow, slow, typical, and every so combination. And that's some transistors can be faster than others. Some transistors can be slower than others. There can be combinations of you get fast transistors and slow transistors. And then typical is just the average of all of that, right? It's your typical transistor.
So is that means there's different, does that mean there's like, are those the randomness and fabrication or?
Yeah, so fabrication is not entirely deterministic. Process variation and everything, so you're not always going to get the fastest transistors, right? So all of this data is cataloged and linked with the cells. So when you build a PDK library, what this is doing is essentially saying, okay, for this process, bundle all of this data together. So it's merging all the SPICE libraries, it's taking all of the cells and compressing them into a single cell library. It's doing essentially all of that and then giving you, here's your built PDK at the end of the day. So all of the data that goes in is what's manufactured and maintained during process discovery and if in case you need to change cells. And then the PDK output, which is essentially a library which contains a lot of cells and SPICE decks, mostly merged together. So it's harder to edit, but it's more compact essentially. And that's what the tools will use.
I see a lot of stuff here. Like there's SPICE files, there's PNGs, there's .sim files.
Yeah, some of those PNGs should be renders of the actual gates. So if you open that up in a
this is just a schematic.
Image. Oh, that's
These are just schematic symbols.
Yeah, that's some of them have I think that's one of the things that's stripped out during building the PDK. All the cells have a rendered version.
Mm-hmm.
And Trevor, SPICE is essentially a circuit emulation and simulation language. It takes all of these math and stuff and wiggles it and gives you simulation results.
Okay, so how about we go, is it okay if we go through this list of files and you just tell me what random things are if you know? Because it's kind of daunting and it might make some sense.
Yeah. I'm happy to answer any questions.
So I have a CDL file.
Okay. A CDL. I'm not entirely sure what that is actually. I don't think it's mainly used in the open source tooling. I think it's probably there for some tool, but I'm not entirely sure what it is.
That's fine though. And that is GDS files.
Okay, so GDS files originate from the very, very early VLSI layout software, and I'm saying like early from the 80s. It stands for Graphic Design System. It's essentially a specific binary format that holds all of the cell geometry, so the shapes and what layer the shapes are on. And so one of the processes when a PDK is built is all of the cells are squished together into a single GDS file, and that's called a cell library.
So it's basically like the Rubylith, sort of like the actual like graphical.
It's kind of like that.
So can we open that? Is like
we will have to build a tool to open it, but once we do, we can open it and you can poke around it all you want.
Okay. I wonder Fedora has any of these tools, like in the repos.
It might. The first one to look for would probably be K-layout.
Let's see if it's in there. It's not there, okay. What's worth a shot?
Magic. Magic would be the other one.
I think Magic is gonna hit a lot of things that aren't what we want.
Yeah, I mean, it's
Oh no, it's there! Magic
program.
Dock, hold on. Magic Dock is in there, so surely Magic... Wait. It is there!
Oh, yeah, okay, so we don't actually have to build Magic. Magic is probably going to be the worst piece of software you've ever used, just a warning.
So, should I just try opening it?
If you want to try opening it.
I'm just gonna go Magic file name and see what happens. Oh wow, this already looks amazing. I don't think this worked.
It did because you didn't load in the Magic RC.
Okay.
Which is it's how Magic knows what layers these things are.
What should I do?
You can close Magic. What you want to do is you want to pass it an argument. It's single tack RC file.
Is this inside here or?
Yeah. So it is in your Sky 130 libs.tech.
I have A and B. Which one do I want?
I like to poke around with B, A. They're both almost identical.
Okay.
So yeah, libs.tech, Magic, and then you'll see a Sky 130b.magicrc.
Okay.
Right. And then you want to pass that with tac RC file to Magic. Just one tac RC file, all one word. Yep.
Like that?
Yep.
And then...
And now Magic knows what things are doing. And yeah, it's a horrible application.
So can I just open the... What path did I have there? It was libs.ref.
Yeah, it'd be in libs.ref. And
I was looking at I/O
and
for
you
some
probably
reason.
want...
I was just going by alphabetical order, but... Oh, this one's magic files, not mag files. Wait.
It does want magic files, and that's probably what you should open. By default, magic files are plain text documents that essentially are like GDS files, but they're just ASCII text.
Okay, so just pick a random one from here?
Yeah, I wouldn't go in the PR, that's your primitive library, so that's where all like the single transistor and all of the spice decks are. I'd go something more like if you go up the hierarchy to libs.ref, yeah. I would go for something like the SCHD. So that's the FD stands for Foundry, SC is standard cell, HD high density.
Okay. By the way, I will give Magic credit for one thing. This is high DPI, and it worked. That's better than Keitra the other day with Java. I didn't have to configure it for high DPI.
That it worked.
Like the text is a reasonable size.
Yeah, I'm honestly surprised because I've had so many problems with Magic. But yeah, if you go into the mag folder, these are all your cells.
What should I pick?
You can pick anything. Zors are pretty fun to look at. Nans are pretty good.
Oh, cool. So this is literally like the chip layout.
Yeah. So that's the actual geometry of the gate.
I don't know how you zoom in and out, but that's okay, I guess.
So it's in the notes. So zooming in is Z, zooming out is Shift Z.
That's very retro.
Yeah, and then you can do Control Z to zoom to selection.
Control Z? Who came up with that shortcut?
This tool is from the 80s. I don't know. And then yeah. So if I pull up my notes here.
Wow, this is super retro.
Yeah. So left click is you set the bottom left corner of the selection or move the selection. Right click is you set the top right corner.
That's amazing.
And then if you hover over blank space and press S, it will select everything. Or create a box the size of everything.
Oh, interesting. Okay.
So yeah. This is magic. And this is what we're going to probably draw our first cell in.
That's scary.
It's actually not that bad once it's set up properly. It is pretty bad, I won't lie, but you know, it's not that bad.
Okay, so I think I'm probably getting ahead of myself a bit. Let's go back to the file list just so we see what's in here. So now we know what GDS files are, even though we haven't opened a GDS file because... How do you even open a GDS file then?
Magic can do it, but there's a special command in the GUI to open the cell libraries.
That's interesting.
Yeah, you gotta use the...
Oh, read GDS. Okay, there's a read GDS thing. I'm just gonna try it just to see what happens.
A GDS library.
I don't know what that did.
It read the GDS and ingested all of the cells, so now it knows about all of the cells in their layout. So a GDS file can have multiple cells in it.
Okay, so I guess it's like an archive, I guess.
Yeah, it's kind of like an archive. I don't remember how to view a specific cell, but there's a way to bring up a cell view. Traditionally, it's just done with place instance, and then you place an instance of the cell you want.
But now it's asking me for a magic file?
Yeah, that's if you want to place an external instance. If you want to place an internal instance, you have to use the command line, and the command is get cell.
Get cell?
Yep, get cell, all one word, and then the name of the cell.
And there's no tab completion?
Nope.
Okay, looks like that did something and it just put it on top of everything.
Yeah, it will paste it wherever your cursor is.
Okay, let me try that again. Okay, now I put it there, but it doesn't actually show anything.
Yeah, so it's hidden by default. If you hit X over the cell, it will show you the contents of that cell.
Okay, that one's pretty big.
It should. Yeah.
That's pretty cool.
Yeah. Yeah, Trevor, K-Layout wasn't available, it seems. That would be having to be built from source, and that's not a fun time.
I think it just broke my zoom forever. No, it's there.
Yeah, it just zoomed in really far. What you can do is you can set the grid to a specific size, so if you go to the command line, because everything's done via the command line.
This is retro!
Yeah, if you enter the command grid, that will turn it on.
I don't
see
a grid.
And then if you do grid space 0.5 0.5 so we're setting it to half a micron by half a micron.
Oh, cool.
There you go. There's a grid.
Nice. So this is 1 micron. This is tiny. What? This is really tiny.
Yeah, these are all small. So this is on the 130 nanometer process, which means it's roughly 150 nanometer resolution because node names make literally no sense. They don't mean anything anymore. But yeah, so it's pretty small, but we're still above the limit where we have to worry about electron tunneling. So, you know, no worries there.
Do I dare ask what that is about?
It's a quantum physics thing where sometimes electrons will just decide to be on the other side of a transistor.
That's scary.
Yeah, we don't have to worry about that until we get into the smaller nanometer ranges. We're safe up here.
Oh, okay. So moving on, we have LEF files,
Those stand for Library Exchange Format. They are part of a pair of formats pioneered by Cadence, which are essentially just layout files. They just describe the geometry and stack up again.
So it's
we have like four different ways of showing these cells, and then we have to have all of them because different tools expect different ones.
This all just sounds so cursed.
Yeah. Again, like I said, this stuff just barely works.
Okay, and then there's lib files.
Lib would probably be all of the Liberty definitions, which are a special type of file for EDA that describe various potential simulation parameters and such. Or they could potentially also be SPICE library files. The lib extension doesn't really mean anything.
For me, it's like library, but I see it's not even library here, it's Liberty.
Yeah. Yeah, it would be Liberty, which is a synopsis file format.
Who came up with that extension? Okay, then we have more mag files.
Yeah, and that's magic, as
Yeah.
we already know.
And then maglev is still mag files, though.
Yeah, they're just more magic files.
And more mag files. You scroll down, so there are a lot of mag files and maglev files, and this is
Yeah.
under the I/O directory, so I guess input output.
Yep, so that would be all your I/O cells, like I/O buffers and all that kind of fun stuff.
So like the pins, you mean?
Yeah, kinda, yeah.
Okay, and then we have SPICE
And then-
files. We already talked about that. You said it's the simulation,
Yeah, SPICE
right?
files are your simulation files, so they describe all of the electrical characteristics of the cells.
Mm-hmm. And then we have Verilog. I've heard that before.
Yeah, so Verilog is an HDL, or hardware definition language. It's essentially kind of like a programming language, but for hardware. And then we have these files which essentially are the functionality of the cells. So if we have an AND gate, the Verilog file will have an AND gate, and it's used for simulating your design before synthesizing it and placing it into an ASIC. So the functionality is the same. And then it also has things called black boxes, which are essentially, they're essentially prototypes, like mock files, which are used in synthesis, so you don't have to copy and paste the contents of the cell, and the logic synthesis software won't accidentally try to gut your standard cells and combine it with your other logic.
Okay, so it's basically like a high-level simulation, and then for like a placeholder.
Yeah, the placeholders are so tools don't accidentally mangle things and wiggle them together in ways that they're not supposed to be. Because logic synthesis tools, when they're doing their optimization steps, they'll look for as many ways as possible to reduce code and make things faster. Black boxes prevent that because they act like a black box, you can't see inside it. And that's important for VLSI because all of these cells are standard cells that will be placed and fabricated in silicon. We can't intertwine them.
Right, because it's already made, right? You can't mangle them, right? Okay. That makes sense. Okay, and then we have, I think this is just another directory with the same stuff. SPICE, maglev.
Yeah, so this is for the primitives, and then the PR stands for primitive, so that's all your transistors and stuff. And then you've got your high density and your
HVL.
high voltage, low leakage.
Oh, high voltage. Okay.
Yeah.
HD.
High voltage
density.
being greater than 1.8 volts.
Right. Quote, high voltage.
Yeah.
And then there's like SRAM macros.
Yep. There's some pre-compiled SRAM macros. There's a whole series of technology called SRAM compilers, which are just a nightmare to work with.
So this is memory, right?
Yeah. Yeah, it's RAM.
And then we have IRSIM,
Yeah.
PRM.
Yeah, so the libs.ref directory is where all of the PDK cell files and simulation files go. the libs.tech directory is where all of the configuration files and metadata files for the tools go. So IRSim is a simulation engine.
A simulation engine for what?
I think it's gate level simulation.
Okay, so which I think, so that's different from the Verilux stuff?
Yeah, so this is actually taking the physical electrical characteristics of the gates and using them for simulation. It's kind of like the SPICE simulation.
Okay. And then we have K-layout, which we already talked about, but we don't have it.
Yep.
I guess this is just config files for whatever's going on there.
It's config files and macros. It has some LVS config files and DRC config files. So LVS is layout versus schematic. So when you're designing CMOS circuits, you tend to make a schematic out of transistors before doing the layout. And then when you do the layout, you can do something called device extraction, which looks at the layout and then tries to figure out all of the capacitors, diodes, resistors, and transistors inside of it. And then builds a netlist out of those, and then you run LVS, which compares your schematic with the extracted schematic to make sure they're the same.
So it's like a cross-check kind of thing?
Yeah, it's kind of like a cross-check.
And then there's a bunch of GDS files and CDL files.
Yeah, I think that's for some Python macros for auto generation of stuff.
And then there's Magic, bump bond generator.
So that's for generating pads for WLCSP. It generates the bits of the layout where you actually bond the little solder balls.
Let me see if I can Google something here. Okay, it's that.
Yeah, WLCSP, or wafer level chip scale package.
So that's actually that what you see there, those traces there, that's actually the silicon?
It's on a layer above the silicon. So the Faraday technology one, which is 2 to the right, has a good side view. So you have the silicon on the bottom, and then you have a stack of Kapton tape, essentially polyamide tape, and some other metals that are above it.
It says RDL
So it's not
Motul. I think they typoed that.
Motul, yeah. It's metal. And yeah, the bond pad, the little bump bond pad is what that
okay, so we are generating the thing under, and then I guess this is a separate step in the process?
Yeah, that's part of the packaging, which is entirely different.
Okay, so we don't deal with this part. We deal with like the little dot on the end only, right?
Yeah.
Okay.
Yeah, it's underneath the glass passivation cut, which is the top layer of the wafer, which is just glass, essentially.
This is so cool.
Yeah.
I don't get what's going on here. Everything's connected together. What? In this package?
Yeah, I'm not entirely sure.
I don't know what's up with that.
Yeah, don't know what's up with that, but that's not a functional layout. But yeah, chip scale packages are some of the smallest ones you can get because they're literally just the die and some extra stuff sandwiched on top. Which also means they're probably one of the cheaper options because you don't need to cast them in epoxy or anything like that.
That's pretty cool.
Answering a question in chat, it does not include the routing for the solder balls. That's done in a separate step.
So when you are making your own chip like this, I guess they, like for a PDK or like for MPW, I guess they just give you the coordinates where you're supposed to put the bumps and then you just put them there? Or... Because if you're not designing the other thing...
Yeah, in the case of the eFabless PDK, the chip we design is actually a submodule into something larger called the Caravelle harness. And it has the pad ring, which is the connection points around the outside. And then it also has a management SoC and some RAM and some housekeeping stuff. But there's a section in the middle which is called the user logic section, and that's where all of our logic lives. Yeah, so this is a good example.
Oh,
that
okay.
blob of logic in the yeah. So there's predefined points for the power grid, but your logic internally can connect up to any. They're essentially ports, right, for the I/O pads. So they're not necessarily concerned about anything that's inside the user space. As long as everything matches up, they have their separate tooling and layers and stuff for the full integrated chip.
Okay, so they give it's like a test harness kind of, right? So they give you they give you the sort of pre-made connections and whatever's going on at the bottom there. And
yeah, so that's a little RISC-V microcontroller.
Another RISC-V. So wait, if you make a RISC-V design, you get one for free.
Yeah, basically.
That's pretty funny.
That's also how they tell the designs apart. So you get 40 projects on a wafer. How do you tell which chips belong to who? Well, each chip has a little bit of. It's Pico RV32. It's actually Vexi RISC. They stopped doing Pico RV32 in MPW5, MPW4. I'm pretty sure it's Vexi RISC now. Sorry.
I have no idea what any of these things are.
Yeah, so there's a little fuse or configuration bits to set your project ID that the RISC-V microcontroller can read out.
Oh, so they actually find out like by probing the RISC-V?
Yeah, it's called it's a housekeeping SoC essentially. It controls. There's also an integrated logic analyzer. I can't remember if it has 256 or 512 independent little wiggly wire ports. There's some SRAM blocks. There's a bunch of stuff, but it's essentially to make the eFabless's life easier for identifying the chips, and also your life easier for Bring Up, because you can write a test harness that runs on the embedded SoC that tests your logic inside the chip. This
actually reminds me of something I did on the last stream, because related to the M1, because and I actually realized one thing after the stream. If you don't mind the diversion, I was looking at performance counters for the M1 GPU, and so they have a select mask, like a 32-bit selection for, like, the chip is divided into like domains, I think partitions they called it, and every partition you have a few counters. I think it's like 8. I don't know how wide they are yet, but then for each counter you select like what you are counting, and so there's a select mask, and I didn't realize this during the stream, but they have like different bits set in the select mask, and I realized after what's actually going on is that 16 bits of the select mask are like wires, like they're just like signals coming in from something. And so then there's a number in the other part of the mask that selects a group of 16 wires, and then there's like a counting mode. And I realized that the way it works is that you can count either a single signal, so like how many times an event happens, or they have one where you add up different signals into the same counter. Like if you have 4 signals that, signal like 4 different events, you can count how many times the total. Like if you have 2 active, it increments the counter by 2. If you have 4, it increments the counter by 4. So it's like a Hamming weight thing. And then they have a third mode, which is actually binary integers. So you can have like 8 signals that are a number coming from somewhere, like how many currently active GPU processes there are, or something like that. You know, like how many active like shader cores and that kind of thing, right? And it's actually a number with a number of bits. And then what it does is it accumulates that into the counter. So then you can, for example, if you accumulate how many shader like work groups are active over the course of an execution, and you divide by the total number of cycles, then you know how many are active on average. And I only realized this right after the stream because I was staring at the masks and I'm like, wait, why are there like 3, flags at the top? And then there's like a selector, and then there's like the 16-bit mask, and then I saw what they were doing with the names, like how they were using those, and it just kind of hit me. It's like, wait, these are like literally wires inside the M1 GPU that you're selecting and counting things on.
Yeah, it probably has some sort of integrated logic analyzer.
Oh yeah, they probably have that too. But this is like the regular performance counters. Like this is the stuff that like the Metal GPU debugger uses to tell you like how efficient your app is and all that.
Right.
So it's not even like for Apple to use. It's like anyone can use that on macOS, which is pretty interesting.
Yeah. Oh, excuse me. But yeah, so your design is integrated into this, and it has a little management area that you can poke and do things with. And that's how they also differentiate which designs are which to send out to people.
So, so then I guess like at the edge of this user area, there's like ports or something defined that you hook up to?
Yeah, so there you had a read the docs up. The documentation for this stuff is not great. I really wish they did better. It's all terribly out of date and just awful, but there's essentially around the pad ring there is things to connect up to the I/O so your chip can talk to the outside world.
And for the I/Os, do you get like literally connecting wires to the I/Os, or does it have like a predefined something?
So most of the I/Os have buffers, so they have like input-output buffers. You can set them as inputs, you can set them as outputs, but you can also use them as pure analog, so they're just going straight to the pad.
Oh, so you can have both. You can choose if it's like digital or analog?
Yeah. There's actually a special separate project, so we have the user digital project, and there's a user analog project.
Oh, like that, like the Caravelle thing, you mean, or?
Yeah. For the Caravelle stuff, you can do analog too. There are some muxes, but as Omni said, but muxes are basically transparent. We don't have to worry about them. Big asterisk there, but
Okay, I don't know what this is about, but we'll go with it. Okay, I think we mostly ran out of things to look at. We talked about that bump on generator. I'm afraid to ask what checkantenna.py is.
So there's a thing. Antennas are unintentional or otherwise radiators, right?
Right.
You send in electromagnetic energy to an antenna and it broadcasts it out. That would be bad in a microchip where everything is very close together because you might accidentally flip transistors.
Okay.
Also, antennas in general are just hard to manufacture. They cause defects. So antenna checker just checks for very long stubs, essentially. A stub being a wire with no endpoint.
Why would you have that?
Accidents, oversights, a tool going wrong. Sometimes they just happen. So the cells are Legos that fit together, so they have little bits coming off them, right? So when you plug the Legos together, there might be some little bits that are just hanging off and not connected to anything. Those would be antennas.
Okay. And then there's checkdensity.py. I guess that's just
that would
like
be checking your cell density.
Like how much stuff you have? Because you can't have too much, or?
Yeah, so the higher the density, the harder it is to reliably manufacture transistors, essentially.
And then they have generate fill. I think I can guess what that is. It's like filling up empty space or something like that?
Yeah, so PDKs have these special cells which are essentially, they can be things like decoupling capacitors or diodes, but they essentially take up empty space, so there's not large voids, which would also cause defects.
It sounds like everything causes defects.
Yeah, like I said several times, this stuff just barely works. It's all magic.
It's
and
kind of
everyone's
scary.
trying their best to keep it together.
That's kind of scary. And then we have run standard DRC.
Yeah, so that just runs the traditional DRC, so make sure
what's a
your level
DRC?
layers aren't too close together.
What's a DRC?
Design rules check. So it's essentially checking the rules to make sure, okay, these two bits of metal aren't too close together, they're not too small to be manufactured, that kind of stuff.
So that's like literally the I guess rules, right? So the constraints for what you're allowed to do and what you're not allowed to do, I guess?
Yeah. Yeah.
And then there's a CO ring generator, which also sounds like something cursed.
I am not entirely sure what that is, honestly.
Okay,
We'll
skip that. And then we have NetGen, which has tickle files in there, which also scare me because I know that's a programming language that tends to be used by cursed software like this.
Yeah, so NetGen is an LVS tool, or layout versus schematic, like I was talking about earlier. And it's just a dedicated tool to do that. So you give it 2 netlists, and it checks to make sure they're the same.
Okay. And then we have spice stuff, which we did talk about. I see .bin.csv files, which also sounds like something really cursed.
Yeah, to see the certain simulation data, you need to just populate it. So you just, stick some binary data in a CSV file and stuff it into the spice engine, and it's all good.
Okay. Open lane. What's open lane?
So open lane is the magical set of tools and scripts that actually take a digital design in something like Verilog and transform it into an ASIC.
So is this the compiler?
So, it's kind of like a compiler, yeah. Except you put a programming language in and you get a picture of silicon out.
That's really cool. So then this is the configuration for actually using the standard cells with open lane?
Yeah.
So there's a lot of stuff here I don't know, like caliber and spef extractor.
Calibre is the Calibre rule deck, which is for part of that cadence suite that I was talking about earlier.
I think we'll skip that one then. Okay, and then we have Verilog. So I'm guessing these are like the either the black boxes or some kind of stand-ins for the
so OpenLane uses a tool called Yosis to do the technology mapping and
I've heard that one.
synthesis.
That's like FPGA stuff, right?
Yeah, but you can also make ASICs with it.
I didn't know that.
Yeah, so OpenLane uses Yosis to take your HDL and does a technology mapping, which then translates the basic cells, the AND gates, the OR gates, etc., into standard cells. So that's what these map files are.
Okay, so I guess so you go from Verilog high level to like normal gates, and then you go to standard cells?
Yes.
Interesting. So there's a bunch of that, and then there's Qflow with PAR files in there. These are literally shell scripts.
Yes.
Oh my god.
Qflow is the predecessor to OpenLane. Suffice it to say, it really probably shouldn't be used.
I want to see how cursed these shell scripts are now. Wait. What shell?
It's tickle.
That doesn't look TCSH. It's tickle SH.
Yep.
Oh no. Okay, fine. And then we have we were at OpenLane, Qflow, X Circuit. How many tools do we have? This is crazy.
There's a lot of tools. So X circuit and
So
X.
you can tell this is ancient because it
X-
starts with an X.
Yeah, X circuit and X schem kind of go together. They are for schematic capture. So this is on the other side of LVS, where you design your gates using transistor symbols inside X schem and X circuit. I don't recommend using them ever. They're terrible and awful, and I recommend using KiCad instead because I made a KiCad library.
I was gonna say KiCad sounds like a lot nicer. I've messed with that before.
Yeah, I made a KiCad library which essentially has all of the PDK symbols and stuff turned into KiCad symbols.
Oh, nice! That's really awesome.
So you can use you can use the schematic capture for KiCad to do simulation and all this stuff. So
That's
you
really
don't
nice.
have to touch X scale.
Okay. Well, I'm glad you did that. I'm scared of things that start with an X.
Rightfully so. But yeah, so that's everything that's in the PDK.
Cool.
Open Lane has all of these bundled, and they ship a Docker container, which should have everything pre-built and ready for logic synthesis. But you really shouldn't need that unless you're going to do a full HDL to.
Remember,
ASIC
I'm on
flow.
ARM64 here.
I think there is an ARM64
Okay.
voice of the container. I checked earlier today. I think I saw it.
Okay, that's nice. So, what should
Yeah.
we do next? What's the plan?
So with all of the explaining done, how do you feel about drawing your first gate?
Sure. I mean, I don't know what I'm drawing yet, but if you can tell me how it works.
Yeah, so we can draw a very simple CMOS inverter. So what it would do is take a high signal, turn it to low, take a low signal, and turn it to high.
So wait, let
and
me
it does
Google that first.
Okay, yeah.
I think we're gonna need a picture for this.
Yeah, so it's essentially formed out of a single PMOS and a single NMOS transistor stacked on top of each other.
Okay, like that. Okay, that makes some sense. Okay, so
Yeah.
okay, so we have ground and we have the supply voltage, and we have two transistors.
Yep.
And then it just goes in and out.
So it's essentially the gate of each transistor is connected together. The drain of each transistor is connected together. And then the source of the PMOS is connected to your supply. And the gate of the source of the NMOS is connected to ground.
That makes sense, I think.
Easy peasy.
So when
Yeah.
the voltage is high, it turns on the NMOS.
Yes, when the voltage is high, it pulls the gate. It energizes the gate for the NMOS transistor, which then pulls V out to ground, essentially.
And then when it's low,
Yep, and when it's low, the PMOS gate is energized, which then pulls it to supply.
okay, I think that makes sense. Also, Mohammed Gabber says we do build for ARM64. That's really cool. Yeah, if that runs, if it's Docker, it should run on Linux fine. I think. I've never tried Docker
I
on
didn't even
Fedora,
realize
but
there was
yeah.
someone from the OpenLink project in chat. Cool. I hope I'm doing it justice.
Okay, so what should we do?
Yeah, okay, so
Wait, hold
let's
on a second. If
go-
we are drawing an inverter, it means we are not using a standard cell, right?
Nope, this is going to be drawing all of the silicon, the polysilicon, and everything by hand.
Cool. I have no idea how that works, but okay. What should I do?
It's okay. I have instructions.
Should I close magic?
Yeah, I would close magic, for now. Also, that is the worst worded dialogue ever. So then in your... we'll probably want to create a working directory for all of this stuff.
Sure. Outside the PDK,
Yeah,
right?
so- yeah, outside, but we got to make sure that's still set, because we still have to run magic.
I think think it's fine. Yeah.
Yeah, okay. Maybe it would be also worth adding an alias for invoking magic with the RC file, because every time you run magic, you'll want to do that.
Okay, so we are... That was in that whole mess, right? In, this
Sky 130, you can, it's sim-linked, so you can just do pdk root sky 130a / libs.tech. You don't need the volar.
Oh, okay. Sky 130A. Like that. Okay.
Tech magic. Yeah.
And what should I call this?
This is specifically magic for Sky 130. So
I guess Magic 130 or something like that?
Yeah, that works. There's also another PDK, which is for Global Foundries 180 MCU. So yeah, that's fine.
Let me just put this in here so we don't forget it. Okay.
Yeah. So we'll want to start up magic then. In the in here is fine. We can just clean up later.
And no arguments?
And just the no arguments. Just start it up. All right. So you might want to resize it until it looks a little better. So now what we'll want to do is set up the grid and DRC and everything. And what you can do is, instead of having to reselect that window every time, you can do a shortcut of invoking it with colon. So if you have the layout window selected and press colon, it will automatically switch to command input mode. And then you can type the command. So
oh,
grid,
it does. Oh, it doesn't actually change the window. It just goes to the wow. Okay.
Yeah. Oh yeah.
It's very
escape
Vim.
and stuff doesn't work.
Okay, I was gonna say it's very Vim, but I guess I see it's only partially Vim.
It's only partially Vim. Yeah.
Okay.
It is so terribly, terribly bad.
Oh yeah. Are we doing a? Oh yeah. Oh yeah. I did 130. You said you wanted to do a Magic 130B. Let me just go to B because. Oh yeah, why did I have Magic 130B? Ah, that's weird. Okay, sorry, hold on. Let me fix...
Yeah, that's probably why Magic didn't load.
I was confused. I think that makes more sense. I am dumb and I did the wrong thing. Okay.
Not dumb, it just happens.
I think that is better now.
Okay. So yeah, so we can turn on the grid.
And you said that was grid?
Yeah, grid, and then we want to set a little finer grid here. So we want to do 0.5 or 0.05 microns. Yep, 0.5 by 0.5. I'm not sure if you can do just the 0.05, but I still think you have to do the prefix 0 because I don't think Magic handles that.
Oh. Ah, it didn't change.
Okay, so maybe it does. Okay, so now.
Okay, yeah, it is right. Yeah, this is just looking at the coordinates there. Looks right.
Yeah. So the next command is snap user, and that turns on grid snapping for the box.
All right.
So now when you click left or right, it should snap to the most nearest coordinate.
Ah, like that.
Yeah. Yeah.
Cool.
Next, we want to enable DRC. So the command for that is DRC style, and then it's DRC parent.
Is it one word
so
or 2 words?
2 words.
DRC style?
Yep, DRC style, and then the next argument to that is DRC open parentheses, full close parentheses.
What? Sorry?
Full.
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 Yeah.
Full.
Full. Full.
Full. Okay.
Yes. All right, and then DRC on. Okay, and now DRC is enabled. And if you look up next to the device 2 button, It says DRC equals 0.
Uh-huh.
We don't have any DRC violations. We're all good.
I would hope so, because it's empty.
Well, you never know with these tools, right?
Yeah.
So let's create our first transistor. So we'll be drawing an NMOS transistor first.
Exciting.
So we want, yeah. So we want first to draw the gate. So we want a box that is 0.15 microns by 1 micron in size. You can do this with the box size command.
Size?
So box size, and then the size of the box you want. So 0.15 microns by 1 micron.
0.15 by 1. Okay, so that's pretty big.
Okay. And then you might want to zoom out, and then you can scroll up and down. So that is going to be the gate for our transistor. Now we need to paint it with our polysilicon layer. So the command for that is paint space poly.
Cool.
And there you go.
So this is literally a text-driven vector graphics program.
Yes, essentially.
This is crazy. Like, why can't I just drag and paint it?
You can manually do the size of the boxes. So if you want to count boxes, you can do that. But it's actually once you're
easier,
used to it,
actually, this reminds me of Blender. I've used Blender, and you can do the same thing, right? You can type the sizes of things, right, in text, Yeah.
So now we want a new box, and this time we want 0.5 micron by 1 micron. So if you remember the command for that,
by 1 micron?
Box size. So we're specifying a size.
0.5.
We want 0.5 micron by 1 micron. So this will be our end diffusion layer, but we want to align it properly. So if you left click, I believe, at the corner of the polysilicon, so it's just on the edge. And then if you paint that end diff.
End diff, 2 Fs or 1 F?
End diff, that's the end diffusion.
1 F or 2 Fs?
2 Fs.
Okay.
All right, and now you notice all of those white dots? And then you'll notice DRC is complaining.
Yes.
So now's a good time to show you how to check DRC.
Sure.
So with the box selected where the dots are, if you enter the command DRC Y, as in you're asking it a question, and then if you hit enter, it will tell you. It should have told you.
Didn't say anything.
You might have to enter the command manually because it's very picky when it lets you do colon commands.
Oh?
Yeah, so if you do DRC Y, why is it not telling you? It should be telling you, magic moment.
Magic moment.
All right, that's normally how you ask it what's wrong with DRC. It's cranky and doesn't want to tell us right now, apparently. So using the same box size, we want to paint end diffusion on the other side of the polysilicon.
Wait,
yeah, Trevor got the...
Okay, end diff on both sides, right?
Yeah, end diff on both sides.
Wait. No, that... What did
so this is a problem with magic.
Okay.
If you click inside the drawing window, like use your mouse and move the box and then move it back, and now do a colon command. Colon paint end diff.
Is it so cursed?
Yeah, it's cranky. Okay, so now we painted the end diffusion on either side of our transistor. Now what you can do is, if you want to manually change the size of the box, if you want to select the polysilicon area, so left click on one side, right click on the other corner.
And this was the gate, the red part?
Yeah.
Okay.
So what we're going to do is we're also going to paint this with end diffusion, which will set up the proper magic stuff to turn it into an NMOS transistor. Yep, okay.
And we got like an edge around it.
Yeah, so that's DRC complaining that our polysilicon is not long enough. So what we need to do is extend the polysilicon by 3 grid units up and down. So if you want to make a little box that's 3 by 3, and then paint that as polysilicon.
Is it poly or? Oh, I
Yep,
need to.
paint poly.
Oh, it's the click thing again.
Yeah, magic is a terrible tool. That's why I'm writing my own. All right.
Okay,
and those
DRC is
DRC
less
warnings
cranky
went
now, but it's still cranky.
away. It'll be very much less cranky once we do the next thing.
Okay,
So now we want a box.
hold on. I'm just
that
curious.
is-
Is this still broken? Oh, now it says no errors found, but here it says 2.
because you have to select the error area that has the errors.
Ah, can I just do like that?
Yeah.
Oh, now it says something.
There you
Okay. End-diff distance to P-tap must be less than 15 microns.
Yeah. So it's complaining that our NMOS transistor isn't a full NMOS transistor, but we're getting there.
Okay.
So now we want a box that is 0.4 by 0.9 microns.
0.4 by 0.9?
Yep, 0.4 by 0.9. And then we want to center that in between the left end diffusion.
There?
So yeah, right there. And we want to paint that with local interconnect. So paint LI. And then we want to do that on the other side as well.
Cool.
Yep, so now that's the local interconnect, which is one layer above the silicon that we'll use to connect our transistors together.
Okay, so we have end diffusion all throughout, and we have polysilicon for the gate, and then we have local interconnect. And so local interconnect is that like layer to layer?
It is intercell connection. So you can think of this being like a layer cake.
Okay.
And this is like one step above the layer cake. It's more foundational. I guess another would be highways versus local roads.
Right.
Local interconnect is like your back street neighborhood roads,
Right.
if that makes any sense, or floor tiles.
We'll go with
Alright,
that.
and now we want to paint our N-well connections to the local interconnect. So we want a 0.2 by 0.7 micron box.
0.2 by 0.7?
0.7. Yep. You'll want to do box size.
sorry.
That just tells you.
Oh, I'm clicking buttons. I hope I can close that. Okay.
Magic is a special kind of application.
Okay, 0.2 by 0.7,
Yep.
right?
Yep, and you want those in the center, and we want to paint that with NDC.
Both sides?
And that's essentially the local interconnect to N-well connection. Yep, on both sides.
Okay.
Alright, and now we have a connection from our N-well. So we have the drain on the left, the gate, or the drain on the left, the gate in the center, the source, drain on the right, gate in the center, source on the left. I'm sorry. Okay, and now we want another 0.5 micron by 1 micron box, because what we're going to do is we're going to be painting the bulk for the transistor, which is the P area it was complaining about.
0.5 by 1 micron, right?
Yes, it was 0.5 by 1. The same size as our N-wells. And
Okay.
it goes right next to the leftmost N-well.
Next to it or on top or
Next to it. Right next to it.
right there?
Yep, and you want to paint that with PSD. Polysubstrate
PSD.
diffusion.
I'm
Oh,
not sure that did
it
it.
did it again.
Oh, that.
You gotta move it and yeah. There we go.
There's
Okay.
still complaining.
Yep. And then what we want to do is we want to expand the local interconnect over to the polysubstrate. So yeah, from one grid square in, you can draw a box to the other corner, and you want to paint that with local interconnect.
It did it again.
It's a wonderful tool, isn't it? And then with a 0.2 by 0.7 micron box, just like we did for the NDC contacts, we want to do another box that big.
On the other side, or?
No, so we're doing a connection from the P diffusion substrate up to the local interconnect. So we're connecting the source and the bulk of the transistor
Was it this
together.
one?
Yeah. It's that size, but it's a different connection.
Right.
So in this case, it is PSC is what we want to paint it.
I'm already lost. But DRC is not complaining anymore, so...
So that is an NMOS transistor.
Huh.
You made a transistor.
Awesome! We made a transistor!
Yeah, it took a minute, and the tools were fighting you along the way, but you made a transistor.
Okay, wait, hold on. Let me go back to the Wikipedia thing, because I still don't get what's...
what? Yeah, that's fair.
This,
Yeah, there we go.
Okay,
That's
so, hold on. It's an NMOS, right?
Yes, so we just drew, well, you just drew an NMOS transistor.
Okay, so can you walk me through the layers? Because I'm still, I kind of forgot already what we did. So I remember the polysilicon gate,
Yep.
which is this part here, right?
Yep, that's the polysilicon gate. That's the red line.
So what's, where's the insulator? The silicon dioxide?
When you painted the end well underneath the polysilicon gate, Magic automatically set up the properties for that to be noted.
So that one's like automatic.
So some of this is automatic, and you'll see in a second, it'll be a lot faster making the PMOS transistor because Magic knows how to do some shortcuts that are really helpful for us. As much of an arcane pain in the butt it is, it has some helpful features.
Okay, so I get the gate, and then we did the end well, but I don't see N. That was in the other. I think the other drawing had that more clearly. If I can find it again. Is it? Oh no, wait. That's the PMOS has an N well, but an NMOS doesn't have an.
No. So when we're making a PMOS transistor, we have to artificially dope the wafer with N-type material.
Okay, but we made an NMOS, right?
Yes, this is an NMOS transistor.
Okay, so what's the green thing?
That is your N diffusion. That is the N plus areas.
But here they aren't under the gate, though.
It shows them as not under the gate, and they're not technically manufactured under the gate, but it's still there.
What does that mean?
This is a simplified representation. It's a lot less clean than that. But suffice it to say, there is no N diffusion underneath the gate.
So then why do we have to draw it underneath the gate?
That tells Magic to set up the conditions so when eventually we do send this for fabrication, that the oxide mask is done correctly.
So that is so it's kind of like a macro that then becomes this part here.
Yeah, it's kind of like a macro.
Ah, okay. This is complicated. There's layers here.
It is. It's not the easiest thing to grasp, especially at first. But you can now say you drew your first CMOS N FET.
Okay. So then let me just go through everything again. We also have the P plus. So this is actually the same color, conveniently enough, right?
That's convenient. It's a peach. Yeah, and that is the P diffusion, which is essentially extra. I think is it boron? I think it's just extra boron.
Okay, so
it's just more strongly doped.
Yeah. So and that was for the bulk connection in that case. Yes. But also the bulk. The bulk is literally the chip under it, the P substrate.
Yes.
So if I make another one of these somewhere else, they're both connected together underneath?
Yeah, electrically they'd be connected together technically.
So then why do we have to connect these together? Because this is connected together, right? Why do we have to connect these together to make a transistor?
That's a good question. That's getting into the more transistor and EE physics that I don't actually know. I just know that they're most commonly connected together for transistor reasons.
We'll go with that. Okay, and so then the...
Yeah, I'm not the best teacher. I apologize.
Okay, so then we have... These are just like, I guess, vias or something? Like going from the underlying...
You can think of them as vias.
Okay.
They're vias which go up to the local interconnect layer.
And then the local interconnect is what?
It's a metal, or sometimes it's another polysilicon. It's just an electrical conductor that is above the next passivation layer. So that second diagram that's showing underneath the magic window on the Wikipedia article shows it pretty well. So it's showing the process. Yeah. So the deposit metal step, that's the local interconnect.
I don't know if I can zoom into that.
Yeah, I don't know.
Okay, there we go. Okay, so you make... So it starts with an oxide. You make a hole in there. You add the N wells, which is this part we said.
Yep.
And then it... Okay, so this is the gate, and you put on polysilicon, and then...
Yeah, this is showing you creating an N and a P type MOSFET.
Okay, so the N well was for the P type. I keep mixing that up. So these are the... Okay, so this is the actual N, this part here. And...
Yep.
So you end up with polysilicon on top of the gate, and then you... Nitride is just... insulator?
It's a passivation layer. It's yeah.
And so here you have polysilicon and then metal on top, and then here... Okay, so in this case, the local interconnect is metal, I guess?
Yes.
Okay.
So that dark gray stuff would be both the vias and the metal shown together, essentially.
So why do we have polysilicon for the gates and then metal for the local interconnect? Like,
It has to do with some semiconductor physics I'm not too keen on, honestly. Unfortunately, this discipline is as much technical design with gates as it is chemistry and physics, and I'm not so keen on the other two personally, unfortunately.
Okay, so what do we do now?
Okay, so now we need to build the PMOS transistor. So there's a really quick and easy shortcut for this. So what I would like you to do is draw a box around the entirety of the transistor.
Including
the polysilicon.
Yep.
All right, and then I want you to type the command select area. Yep, you can hit enter on that. And that selects all of the geometry in the box. So now we are going to duplicate this transistor. So there's a command called copy, which will copy all of the geometry, and then you give it a cardinal direction. So in this case, we want to copy north, so N. And then we give it grid units to copy up. So 32 in this case. It's a magic number, but that's because I tested this beforehand. Yep. All right, so that duplicated our NMOS transistor. But we still need to turn it into a PMOS transistor. So to do that, we want to make the box a bit bigger. There's some magic numbers I divined, but basically we need to make the box 1 grid space bigger on the top and the bottom, and 5 grid spaces bigger on the left and the right. You could do this manually, or there's a grow command. So box grow, and then the direction. And
I think I just did it manually.
Yeah, that's fine. And then we want to paint N-well under that. Yep.
Cool.
And that turned it into a PMOS transistor. You now have a PMOS transistor.
So that's literally the only difference is whether there is an N-well or there isn't around everything.
Yeah, well, you still have to make sure that the layer data is correct for manufacturing, but Magic did that for you.
So it automatically knows that if it's inside an N-well, it'll be P doping instead of N doping.
Yes.
Cool.
Yeah. So now we want to connect the gates of these transistors together. So you can draw a little box for the polysilicon.
So that'll just be polysilicon connecting the gates together?
Yep, that's just polysilicon.
Is it draw or
you can middle
paint?
click. Here's a quick tip. You
Yeah.
can middle click over any already painted area to paint your selection that.
Oh, cool. Oh, that's handy. That's really
Yeah.
handy.
Yep. And so now we also need to connect the drains of the transistors together.
Which side was that?
That would be on the right. So we want to draw a 4 wide box. You could do it that thick. You're probably going to run into DRC errors. I would recommend shortening
Okay,
it
so
up.
you want to do it like that.
I would do it on the very edge. But
Oh, okay. Like that?
yeah, and then you want to paint that local interconnect. Yep.
Can I just middle click or doesn't? How does it know when you have
You can
multiple
just
layers?
double-click
Okay.
that. Whatever's the visible layer.
Okay.
Why is that complaining? That shouldn't be complaining. You want to select that and figure out why DRC is cranky? Paint DRC. Oh, it's angry at you again.
Hold on. Let me see if I can just. Okay, PFET cannot abut end diffusion. End diffusion spacing to N well. End diffusion distance to P tap.
That's not right. So if you want to hit U to undo, and then undo, 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 undo. There we go. What if you manually paint that with local interconnects?
Oh, okay. So it didn't actually pick the right layer.
Yeah.
Okay.
Sometimes it does. Sometimes it doesn't.
Cool.
All right.
Alright.
We should probably make a metal port or a port for all things. So, this as it stands technically is a fully functional inverter, right?
It's just not connected to anything.
It's just not connected to anything and it's not easy to connect it to things.
Mm-hmm.
So a common way to do that would be to sort of turn it into a standard cell layout.
Mm-hmm.
And we can do that if you want to continue on this.
Yeah.
Okay, so what we will need to do is first we want to make a 0.4 by 0.4 micron box. And we're going to
0.4 by
create
0.4.
Yep, which is yeah, it's like 8 cells.
Yeah,
By
8
eight
by
cells?
8, yeah.
And we want to stick that on the bottom of the polysilicon on the gate.
Centered on that?
Off to
it's-
the edge. The
Yeah,
corner
because
line.
we're not, yeah. This is not even.
Other corner, but yeah, that works.
Here? That?
Yeah, there you go. And you paint that with polysilicon. And then you want to also paint that same size box with your poly connect. So the layer for that is, for local interconnect rather. So we also want to paint that with local interconnect.
So will that
And
create
now
a
we want to
connection?
do-
Or do we need a...
We'll do that next. So that's
Okay.
poly contact. So we want a 0.2 by 0.2 micron box for that. So 4 by
Just
4
that?
grid
Yep.
space. Yep, in the center, and paint PC on that.
Cool.
And that's, yep. And then what you can do is with a 1 micron by 0.2 micron box, we're going to create a little tail.
Uh-huh.
And that will just be the A port. So you can bring that over to the very edge of the transistor on the other side. So this will be A.
Yeah.
Yep, and that can be there.
And just paint it
And that's
local
going to be
interconnect?
painted with, yep, local interconnect as well. And then we're going to pull out the local interconnect from the drains up to this area. We're not going to connect them, but we want to kind of put them in the same plane. So when we tile these cells together, they'll automatically connect.
Right? So,
So
same
I
line as
think
there?
The magic. Yeah, but on the other side.
Oh, the drains.
So we're connecting the drains to this little bit.
So here.
Well, we'll want to put it at the bottom, so you'll want to bring it down to the same plane. So
Okay.
what will happen is when you tile these next to each other, they'll connect.
Okay, so then we're 4 by 4 units from here?
Yeah,
or...
I think the magic numbers I figured out were 0.5 by 0.2 for the first box.
Like that?
Yeah, and that should bring you to the edge of the end diffusion. Is kind of what we're looking to line up our rightmost with the end diffusion.
Okay, so where on the left side or the right side?
On the right side.
Okay, and
so
where?
we'll want the very edge of the local interconnect to line up with the external end diffusion on the PMOS. Sorry, this is not clear, is it?
I don't know where I'm supposed to click.
So you want to put it in line. You want to inset it so the 4 in from the edge. I am doing absolute garbage at explaining this. I apologize.
Here?
Yes. Pull it in 1.
So
there?
4
Yeah,
in
there,
from the edge
okay.
of the local interconnect.
Yes, I'm sorry.
Okay.
Gosh, I am... Words are hard.
And local
we
interconnect?
want to paint that local interconnect. Yep.
And then it goes up, right?
And then we want to... Yep, and then we want to connect it up.
And now DRC is complaining again.
Yeah, you might have to manually paint it.
Wait, why is it a different color
why.
now?
Why
Oh, is it because it's poly? I think it's copying both layers or something.
Oh, it very well might
How
be.
do I delete that?
There is an erase command. So erase and then what you want to erase. So erase poly in this case.
So then this also shouldn't be poly,
Yeah,
right?
Okay. Yeah, that should not be poly.
Okay. So, but this is right? The poly exactly.
Yes, that's right.
Oh, okay. So I guess the middle click thing copies everything, not just the topmost.
That might be a setting because I swear it never used to do that.
Okay.
All right. Okay. Now we're going to draw the metal layers, which is what we will use for distributing power. So these are going to be big chunky connections over the source and the bulk contacts on each of these. So you want to make a big box from the edge of where the local interconnect is on the bottom cell. Yep, and all the way up to the left edge.
To the exact edge of to here, or?
Yep, and then same on the right. So
Are we
you wanna make
overlapping
box
the entire local
Yep.
all the way
All
to
the way.
here?
up even further. So all the way to the other edge of the little local interconnect hub.
Oh, okay. This is like a bus
yeah.
bar type of deal.
Yeah. We're making bus bars essentially. So we'll want to paint that as metal 1.
M1?
So paint M1. Yep.
Hey, I know the M1.
Yeah, and then that exact size box will work for the PMOS transistor as well. Yep. And now we need to make the vias. So you can just select the little box over the local interconnect vias.
The smaller one here?
Yep, you can just make that, and then the paint MCon. So that connects metal 1 to local interconnect.
And end two ends or one?
1 end.
Huh.
And then you want to paint the other one next to that as well. Same thing. And then the 2 on the bottom as well.
So then we have double connections, right? Because the local interconnect is already connecting these two together.
Yeah, but it doesn't hurt, and they're basically free, so...
So then you're like having just redundant extra connections for the power?
Yeah, and it allows more current to flow. But yeah, there is your tileable inverter.
That's really cool.
Yeah, there's a few extra steps. We can make labels and then export it, but you might want to save. So you
Yes,
can
how do I save? File save or?
file save works, or the save command and then the cell name. So save inverter. And there you go. And that
Awesome.
would have dropped a inverter.mag file in wherever you started magic up.
Cool. And it's just, okay, it's literally just, yeah.
Yeah.
Nice.
But yeah,
That's actually a very
there you
simple
go.
file
You drew-
format. I like it.
Yeah, and you drew an inverter.
Awesome.
Congratulations.
Yay! Let me zoom in. That wasn't that bad.
No, the hardest learning curve is figuring out what the layers do and how to connect them, and then using the tool. But once you have those figured out, it's pretty easy. But yeah, Magic is a rough tool to use. K-Layout is slightly better, but still pretty rough. So I am writing my own tool to do layout, which takes after KiCad's PCB to hopefully make it a little more ergonomic.
That's awesome.
Yeah, so yeah, there you go. CMOS inverter.
Nice. So what do we do next?
So there's a few things we can do next. We can turn this inverter into a buffer. We can do spice extraction to extract the transistors for spice simulation. Those are the two big ones at the moment.
What do you think that we should do?
I don't know. I'm up for anything.
You're the expert. What's the most fun?
I appreciate the compliment, but I am not an expert.
You are. I don't know any of this.
Yeah, we can finish this up and do a full hierarchical cell if you want.
I don't know what that is, but okay.
So a hierarchical layout is essentially a collection of cells that are in a hierarchy. So like your buffer. So okay, let me start from the beginning. Do you know how a CMOS buffer is made?
I think it's two inverters.
Yes, it's two inverters in a row. So we drew an inverter, so our buffer cell, which is its own thing, would have two sub-cells, which are the inverters you just drew.
I was about to copy and paste the whole thing over, but I'm guessing there's a better way of doing it.
There is a better way. You can just copy and paste it, but if we're doing all the fancy hierarchical stuff, then we should probably do it a little better. Also, hi, Sayan-nyan.
Hey, hello, Sayan. This is not a sorry.
Yeah, this is intense. All right, so we should probably make some labels.
How do we do that?
So there's some special syntax to make labels. So if you want to zoom into probably the local interconnect on the bottom left, just kind of zoom into that area so it's a little bigger. So you'll want to make a zero-sized selection on the very edge in the middle. Yeah, zero-sized selection, which is weird, but this is how Magic does it. So the command for this is label. So we want to make a label. And then we'll call this A, and then we have to give it a cardinal direction for which it's facing. So it's facing west in this case. Just W would be fine. Yep. I don't know if it actually did that. I think Magic's cranky at you again.
Oh, no.
There it goes. All right, and now
that A is tiny. That is a tiny A.
Yeah, there's not really a way to... I don't know if there's a way to fix that. But
okay.
With the selection in the same spot, we now need to turn that into a port. So the command is port make, and then the port ID. So in this case, port make 1. That should have given you some output.
It's still tiny.
Did it turn? It turned an indistinguishable color of blue. I think that means it worked. Okay.
Yes.
So now we want to make the Y, which is the output. So that's on the other bit of local interconnect. You can hold Shift.
Yeah, I already
right?
figured that out. I was just trying to instinctively use the scroll bar and notice it really wasn't working well. So then this would be label Y east.
Yep. And we want to turn that into a port as well. So the next port would be 2. Yep. So that's the 2 ports. Yeah. And now we need to make the VDD and VSS ports. So I think VDD was the bottom one. I don't entirely remember.
P-type is the top, so that would be VDD.
I thought that was VSS.
I thought VSS was ground.
Well, it doesn't really put... Yeah, it doesn't particularly matter. We can call them plus and minus for all we want, but yeah, we want it on the edge A's on.
On this one.
And yeah, about center. And then same thing, create a label and then make it a port.
Uppercase is fine, or?
Yeah, uppercase is fine.
And
then this is facing west. Yep.
And is that
port
3 or?
Yep, that's 3. And we have to do something special for this next one. We have to explicitly tell the label which layer to attach to.
Oh, because there's 2 edges here.
Yeah, so in that case, it's adding the layer on the end. So it would be label VDD West M1.
Ah.
And then we turn that into a port as well. And that would be port 4.
Cool.
All right, and then we want to save again. So make sure you save.
That's an amazing dialog box.
Yeah.
Just right?
Inverter. Yeah, right should be fine. All right, so now that this cell is completely done, so we can make a new cell.
Okay.
So you can click the cell button. New. And now we'll call this buffer. Yep. Okay, so now we are making our buffer. So do you remember the command when you were first messing around placing instances?
Was it the place instance thing here?
Place instance or get cell would be preferable in this
All
case,
right.
the get cell command.
Inverter?
It's all one word, get cell, and yeah, it would be inverter.
Do we need to place a box first, or?
It should auto place a box, but it got cranky at you because Magic is perpetually cranky.
Ah, okay, now we got something.
All right, and now it's created a box the size of the selection, so you want to go to the right edge of this inverter, so bottom right corner, and then run get cell again.
Cool.
And now you have 2 inverters.
Yep.
You can press X to show the contents.
And it lines up.
And there you go.
Nice.
Yep. And then you can save this out to a buffer.
So file save.
File save. The glorious command. Okay, so now we have a buffer.
Cool. That was easy.
Yeah, and because we are now 1 hierarchical level up, we need to recreate all our labels.
Oh no.
Yeah. It's only 4 labels.
On the same as the other side, as the other one on the left hand side.
Yep. Port make 1. Yep. No, where did you put that Y port?
On the right side here.
Yeah, okay, I didn't see it. Sorry, just making sure.
Yeah, it's like tiny. Like both the text and everything is like. Oh
Yeah.
no. I mean that's fine, but not what I wanted to do. Label VSSW. I mean that's fine.
Yeah.
Let me just zoom in and make sure this all worked.
Yeah.
Okay, I think that's. I don't have the colors right. It has an A. It's like purple now or something.
I think it should be fine. In theory.
Theory. This one here. Yeah, they all look kind of grayish. Let me do the top one.
Because we're in a hierarchical setting.
So then here we do label VDDW port make 4.
I don't think it created the label because you wiggled it.
No, it's there. There's a VDD there.
Oh, is it?
It's just the
Okay.
color. Oh wait, no, the layer. I think I messed up the layer.
Yeah,
Because this one
so,
is. How do I delete it?
Erase label, I believe it is.
VDD?
No, it works on selection boxes, so you should be able
Nope,
to just erase
that
label.
didn't work.
I don't know. I've always scrapped the entire layout if I ever do that.
Oh no!
There should be a way to undo the port creation.
Can I just undo?
You should be able to just undo. Yeah.
No, that's
There you
not.
go. It's gone.
No, it's still there.
It's gone. I don't see it.
Still there.
I can't see it.
It's still there.
Are you sure?
Yes.
I don't see it.
No, I could see the text. It's there. I don't think undo worked.
That's a good question. If you just type port into the command line, it'll give us a synopsis for the help.
Port remove. Oh, because it turns it into a port. But I think I didn't even
Yeah.
create. Hold on. Oh, label doesn't do anything.
No. Again, I think it's because you're in a weird state between command. Yeah.
No, that's still not doing anything now.
Mm.
I think it's very cranky at me right now.
Yeah, you made it angry.
Now it's very... Okay, now it says VDD. Okay. Port remove. And now what if I port in a non-edit cell? Oh, is that because it's the hierarchical VDD?
Oh, it might be complaining about that.
Can you label remove? Oh, now it... No, that created a label called remove. Oh no. Oh no. Undo?
Erase label.
Erase label? Okay, that erased it. Oh, maybe maybe that is the hierarchical VDD. Okay, so it didn't create it?
Maybe not.
Okay, so how do I... Okay, so label VDD West M1.
Yeah.
Oh, the color changed so subtly.
Yeah, there we go.
Oh my
now
god.
we turn that into
Okay.
a port.
Port make, was it?
Yep, port make and then port.
Wow,
Okay.
okay.
Now we probably wanna...
So now I don't know if I actually undid the other ones because I just realized that was always there. The text was always there from the... This might...
It'll be fine. In the next step, it'll be apparent if it worked or not.
Hold on, let me just try something. Okay, claims we have 4 ports, so that sounds reasonable.
Yeah, that sounds reasonable. So I'd save the cell again, because we don't want things to get angry. And now there are some special magic incantations to extract it into a netlist.
Huh.
Alright, so the first thing we're going to do is extract all of the transistors and everything. So the command is quite literally extract space all. Yep.
Is it angry at me again?
It's Angie.
Okay, there we go.
Yeah, okay. Alright, now we need to set up some settings. So we want to turn the hierarchy on. So the setting is ext2spice hierarchy on. And then the next setting is scale off. Same thing. ext2 it's the same ext2spice. Yep. Yep. And then just run ext2spice and it will extract the spice net lists. Alright. So now you should have some files in your chip design directory.
Oh, I have a buffer spice.
Yeah, so if you open that up in a text editor, that is the extracted netlist.
Cool. Okay, so it's a sub-circuit
Yeah.
inverter AY with 4 pins.
Yep, those are your ports. And then
Oh,
you
and
can see
it literally
detected...
knows it's an NFET from the Skywater. Like, even though we drew it freehand, it knows what we drew.
Yeah, magic's pretty magic that way. It's pretty good at device extraction.
So
and you can do a whole bunch of cool stuff like parasitic extraction, but that's an advanced topic.
So what would happen if like it's a different size by 1 grid unit?
As long as it still follows the general design of a transistor, it'll be able to extract it.
But wouldn't this be like a
So-
very specific transistor that is drawn a certain way, and if you draw it a different way, the simulation would be different?
It is, but that's what those parameters on the end are for. Those are describing the actual geometry of the transistor.
Ah! So as long as it looks like a transistor and just has certain dimensions, then it can generalize over that.
Yep.
That's really cool.
Yeah, and you can see how the hierarchy extraction worked. It knows that there were 2 inverters, but it only needed to extract 1,
Yeah.
and then it created 2 instances of those. It looks like the labels weren't set up quite properly because your buffer subcircuit doesn't have any ports.
I know I added at least 1 that was right, so I'm not sure what's up with that.
Yeah, I mean, it's not too bad to fix, but it's essentially just making sure the A and the Y and the VDD and the VSS are connected up. But yeah, there you go. You drew your first transistor, you turned it into an inverter, then you did a hierarchical layout to make a CMOS buffer, and then you extracted the devices into a SPICE netlist.
Awesome.
You're already a chip designer.
No,
Congratulations.
I
Time to make the
can't.
M4.
No, wait. It did connect the inverters properly, right? So it's only the pins on the buffer itself that it didn't extract.
I think it connected the internal inverters together in a
Yeah.
weird way.
No, I think it's right, isn't it? Because one output is connected to the...
Yeah, what I think you have to do is instead of inverter underscore 0A, if you add just the A, Y, VSS, and VDD ports to the buffer, and then fix up those names, it'll be perfect.
Hey, can we fix the problem with magic, or is it not worth it?
I think it would involve drawing in the upper hierarchical cell, drawing local interconnect and metal regions.
Oh,
to
you actually
attach
need to
the
do
labels
that.
to. I think you might need to.
Oh, that's kind of annoying.
Yeah, so it's better just to, quickly fix it up here.
What's V sub S? Why did we end up with that?
Yeah, I don't think it detected your the VSS correctly.
I think that should work, right?
Yeah, that should work. And there you go. There's your buffer.
Nice.
Setting up the SPICE netlists and decks would be next. You'd need ng-spice for that. I don't know if that's in your repos.
That's in there.
Oh, nice. You also have tickle spice because, of course.
And I can't type my password. I still can't type my password. Okay.
Okay. Let's see. I'm trying to remember Spice offhand. I've only really done Spice inside KiCad. So I'm not too terribly clear on the raw Spice terminology, but I think we need to include a library for our simulation cells.
We need these, right?
Yeah, we need those. I will get you exactly what we need in a moment. I just have to look it up because I wrote it down somewhere.
Copy paste time.
Yeah. Da-da-da-da. Introduction and first simulation. I made notes for a reason. Because I am a dummy. Okay. So, I will send you the text link because it'll just be easier for me to send you that.
Am I editing the same spice file, or am I doing something else?
Yeah, the same spice file. Sorry, I had to make sure I got that right. Yeah, you'll want to make sure that's pointed to your PDK root up in front of that. So what that's doing is including the typical cell library for spice.
Okay.
Now I have to remember how to actually set up sources and all of that jazz. This is getting to the point where my spice knowledge is shaky because I forgot. This would be much easier in a GUI. That's a good question. So what we need, what we need to do is we need to define a voltage source to connect VSS and VDD to, and then we also need to define something to wiggle A, and then we need to define simulation parameters. So let me just throw this together in EE schema real quick and I'll get you the spice syntax. I apologize.
No, it's okay.
I was not prepared as I thought I was.
No. Don't worry, we can wait.
I honestly expected it to drawing the transistors to take a little long. Not on you, just because it's hard to, you know, hawk this stuff over. The
You explained it really well. We did.
Well, I appreciate that. How did I... Where is this? I'm looking for... Oh, there it is. Don't mind me, I just don't know what I'm doing.
She knows what she's doing.
I wish I knew what I was doing.
She really does.
This might take a minute, so if you want to do some other fun stuff.
Just noticed Lena has 4 ears. So I can hear better that way.
Yeah.
Why wouldn't you want 4 ears?
4 ears are the best. Or so they say. I don't know. And then I want to label
So are we
that
using chips to optimize
A.
making chips? I think that's how it's supposed to work, yeah. Because
Yeah,
they
basically.
use computers to do this, right?
Well, yeah, you used to be able to just draw it on paper. But, that's not done so much anymore. Okay, I think I have Spice Netlist for you.
Spice! Let's go!
Yeah. Okay. So there is the raw netlist. But yeah, so V1 is a voltage source.
Okay, so we have a voltage source.
Yeah, that's connecting up to A, which you might need to connect buffer to A in a different way. Give me 1 second.
Because we don't have a sub-circuit instantiated yet, so we're gonna have to do that, right?
Yeah, so you want to instantiate a subcircuit of the buffer.
And if I'm defining the syntax right, this would be do I need that slash?
Yeah, you can rename ground VSS.
And then you call that 1v8. And
that's just what
ground.
KiCad called it. Yeah, I think that's right.
I'm just following patterns here. I don't know what I'm doing, but I'm just
I think
spelling
that's
it the same way
right.
as that.
The best way I can think to test it is to try to stuff it in ngSpice.
So you still need some way of observing the output, or is it just gonna show everything?
I think it should show everything with the two dot commands above. It was what, save all and probe all I.
I see.
Yeah. So if we just run I think if we just run ngSpice on it.
Malformed line, it did not like that line. I think the Y.
Malformed E line. Oh, it probably wants it X prefixed because it's a subcircuit.
Oh.
So X buff. Yeah, okay. I don't know my ngSpice commands, so we'll probably have to interrogate help if it exists.
Perform matrix transposition of multi-D vectors. I'm scared already.
Yeah, I think we just want to run.
Run?
I'm not entirely sure.
Initial transient
Doing
solution.
Yeah, okay, so it spiced it. Number of data rows. Is there a show or an export? Maybe we can get this in a graph?
Show devices? No. Save event values?
GNU plot. Do you have GNU plot?
I can probably get it.
That'd probably be the easiest way to just yeet it over to GNU plot.
GNU plot file plot args.
Could always just try to run GNU plot.
It wants a file.
Yeah, I don't know.
Google time!
Yeah, sorry, I apologize.
ngSpice tutorial for beginners. That sounds good. And look,
Yeah,
it's an
that's a good
inverter.
one.
We know that one.
Hey!
Oh,
it looks like you can embed the plot stuff internally with the control logic.
well, let's just try typing it out first. Oh, tran. There's a tran command.
Yeah, that's what we did before. So that .tran was the transient analysis.
Wait, we didn't do tran, did we? Or is it here?
That was in the spice
Oh, this
file.
one, okay. So then,
Yeah, so
plot
the dot
int,
control.
plot in, int out. So those are, okay, those are the signals. Okay, so if I just do plot, so if I do something like plot, /a /y, it should give me both.
Maybe.
That didn't work. Is it not like the slash?
Plot in int out.
Oh, is it
Plot
lowercase?
No, I think it's just grumpy at
Can I do that? No. If I do tran first. T-step is invalid, must be greater than 0.
Yeah, so you specify the size of the step and then how many steps to do.
But it doesn't like my plot.
Yeah, I'm not entirely sure why it doesn't like your plot.
PS expression, plot things. What's VDB out? Oh, do we need that?
Oh, I think
oh no, that's again in D. No, that's not what we need.
Yeah, so I think if you do GNU plot a file name.
Oh wait, VDV, is this what we need? VN V6? Those are node names. Okay, hold on, let me try this.
Yeah. Oh, right,
oh,
because you're plotting voltage for...
Okay,
yeah,
now
right,
this one is not doing,
versus...
No,
it seems to be working.
No, I mean high DPI. This one is not.
Oh, yeah.
This one is tiny. I don't know how we zoom in here. Oh, that is tiny. Script SVG.
It's hard to tell if your inverter is inverting.
It shouldn't be inverting, it's a buffer.
Yeah, if your buffer's buffering.
I think it's buffering because otherwise we'd see both. But I think we need to... How do I zoom in here? Oh, okay, right. Oh, okay, that's... Okay, can I get... Oh, okay, that's how it works.
I suspect it's not hooked up quite properly because it looks like...
Oh, no, yeah, the output is like, is like a line. Yeah, okay, so we're not buffering properly.
Oh, well, I believe your buffer works. It's just the Spice Netlist is kind of funky.
Yeah, but I want it to work.
Yeah, I have a feeling that is specifically what we're wiggling at.
Hold on, can I plot the inner... Is there something there in the
Yeah, you should be able to plot the inner.
The inner thing. That's still... Oh no, there's some... Oh, but it's like... No, okay, something's broken, clearly. And this inverter is not inverting and it's not... Huh, okay.
Well, I believe in your buffer and inverters. I know they can do it.
Why?
It might not have worked this time, but the general premise still stands, right?
But I want it to work!
For all intents and purposes, it should work. Why it is not working, I don't know. What you can do is, instead of instantiating a buffer, try to instantiate just an inverter.
Wait, I just realized something. Is this pulse the right voltage?
Oh, probably not.
Shouldn't this be 1.8?
I think that's only pulsing to 1 volt. Yeah, you might... I think that pulse also might be too fast. I forgot to boop the settings.
Tran? Hold on.
It was run or something like that.
That still didn't work. But now at least it's in the middle.
Yeah, I think the pulse is just going far too fast.
And we make it slower.
We have to bap at the Okay, so in order of parameters, it goes the initial value, the pulsed value, and then we have the delay, the rise time, the fall time, the pulse width, and the period.
So that's like 10 megahertz period.
Yeah.
You'd think that would be fine.
The pulse width is pretty small. Maybe make the pulse width something like 100 nanoseconds.
No, but I mean,
to
if
100
the
nanoseconds.
cycle time is 100 nanoseconds, the pulse width should be half of that. So I think that's fine. Someone said try
Yeah.
swapping the supply. We can try that. Oh, I know. That's what I did wrong. I have it backwards. That's what I did wrong. My buffer power supply was hooked up backwards. That
Oh, yeah, that'll do it.
that will do it. Yeah, I think we just let the magic smoke out of our buffer.
Yeah, out of the transistor. Thank you, Omni.
Ah! Oh, I think that looks that already looks like it did something. Oh yeah, look at that.
Yeah,
It's
that's
buffering with
that's
like
better.
little spikes and stuff, which I guess is probably to be expected.
Yeah, that's to be expected. We're also running on the typical model, so you can
Mhm.
switch the TT to something like FF for the fast transistors.
We're done.
So that's on the lib line.
Oh, here. FF?
Yeah, so that's the and these are called corner modules or corner types because they're like the corner cases.
Well, it didn't really change much, but I guess maybe more spikes, yeah.
So yeah, there you go. You have now.
I have
Learned
now
enough-
successfully hooked up a chip backwards to the power supply. That's
Well, that's what simulation's for, right? It's not like we actually turn this into silicon.
Okay, hold on.
Yeah,
Let me actually
but-
plot the inner node. Oh, that didn't work. I don't know how you do that.
I think you want. That's a good question, actually.
Oh, that. I think it was that. Yeah, okay, then you can see the internal node is inverted.
Is noisy, is wiggly.
I think that's the simulation time, right? Like if I
Yeah, that's probably we've probably hit simulation resolution
So if
limits.
I-
'cause
if I
we're
do,
only
like-
we're going in what?
let's do 10 times that.
Yeah, because we're only doing a few nanoseconds.
Oh yeah, that's a lot more. Yeah, so you get some oscillation and stuff.
Yeah, and yeah, I'm not surprised, Trevor. These
But that's
tools are
also the
brittle.
simulation time though, because I can see it.
Yeah, it's aliased.
I'm just curious. I just want to see. Is P for picoseconds?
Yep, P for picoseconds.
Let's do even more. Let's see how slow it is trying to do that. Woo, takes a while, but not that bad. And if I zoom
Oh, yeah, 'cause
into
you're going-
that,
A lot more.
oh, that looks a lot nicer. Still getting like the big spikes there, but now that's very fast.
Yeah, your simulation.
And it's still,
time
yeah,
has-
simulation is
yeah.
still not really like it's still oscillating at the simulation frequency. So I guess that's just what you get with Spice.
Yeah, it's also depending on the model because this is all mathematically based. It's
Right,
just
right.
solving equations, as MM said. So you got damping and all of that jazz.
Mhm.
But yeah, so you have learned a bit about CMOS, drawn your first NMOS transistor, turned it into a PMOS transistor, turned that into an inverter, turned the inverters into a buffer, and then simulated the buffer successfully.
That's so cool.
You are now ready for the next stage of chip design, which is writing Verilog.
I don't want to write very long.
Oh, we don't have to do that now. That can always be for next time because we got a lot done.
I didn't mean that. I mean like can we use Python?
We can. So there's a few options for that. Python is available.
Nice. So should we end it here? Is there anything else I should try?
If you want to end it here, the other option is to try and get OpenLane set up and running and get a test ASIC built. Just one of the samples that they ship for testing OpenLane.
How do we do that?
Okay, so ideally you'll have Docker installed. I don't know if you do.
I do
'cause
not,
all of
but-
the, the open lane tools run in Docker.
We are going to try that.
It's easier for them to do deps because, as you see, these tools
Apparently
are very...
Docker here is Moby Engine. I have no idea what that is, but...
Oh, I have no idea either. But yeah.
Okay. So I've never used Docker.
Yeah, I think you have to add yourself to the... I've never used Moby Engine. I have no idea if it'll work the same.
We'll just try it.
Yeah, I think you have to be part of the Docker group, or you have to be administrator in order to wiggle Docker.
Let's just try it, and if it complains, we can fix that.
Yeah, so I think you have to syscontrol start Moby Engine Docker. I don't know. I have to look this up because I've never done. I don't use Fedora.
It claims to be a
I use
socket,
Arch.
so I think it might just work with socket activation.
Okay. Do you have the Docker?
You might need to do that, but that's really easy. Do I have the Docker what?
Command line utility? Do you have just Docker?
I do.
Okay. So we would want to pull a specific Docker container. Docker Hub eFabless open lane.
Okay, maybe I do need to start it. And okay, it does want permissions for that. That's I want. Okay.
I still can't believe
Why not?
there are this many people watching this.
What? Where's my Docker group? Why is that not? What?
I know. You might have to new group it.
I did.
Oh yeah, we have one of the.
Oh, now we do it. Okay, new group didn't
open
work.
lane people.
We'll take that. Docker PS. Okay, now we're there.
All right. Now we want to pull the eFabless / open lane container. So I think you can just do Docker pull eFabless / open lane. In theory, it will pull the correct architecture. I don't know.
Hopefully.
I've never used Docker across architectures.
Says we have it.
Yay! We should probably clone open lane locally as well. So you'll probably want to clone a local copy of open lane into your chip design.
This
area?
one? Or eFabless? Which one?
Yeah. Yeah, I sent you a link to the Open Road project one.
Okay. Here it goes. That's a lot of megabytes.
Yeah. It be like that.
And this is Aki copying and pasting commands for me to run.
Yeah, sorry about that. I just have ASIC root there as a general variable. That's where your chip design directory is.
I'll do that.
Yeah, that works.
And I should do that.
Yeah, that command in theory should just drop you into the container in a bash shell.
I don't think we want to do that. Oh, is open lane? Oh, I did clone. Yeah, okay. I think that's that's fine. Hey, there's something there.
Yep. Okay. Now, if you do an ls,
Well, that's great. Is my like is my?
It's probably permission.
Oh, my home
things.
directory. Okay, yeah. It probably needs that. Okay, let me do that
You might
again.
have to.
No, that did not work.
Oh, it's probably the user mapping, the TAC-U and the TAC-U, which is setting the user ID and group IDs.
That should work.
Yeah, but I don't know. Debugging Docker is the next big challenge.
So, I mean, it clearly doesn't know who I am, but it has the right ID inside it claims. But it doesn't work. Nor the PDK.
Yeah, as Mohammed said, going into the OpenLane folder and running make m is the endorsed method, but I
Here?
don't like their make file. No offense, but I just don't like your make files.
Oh, and it's pulling a different one.
Yeah, in theory, I think this will do...
But that doesn't fix the permission problem. It just
Yeah,
mounted
no,
it
it's still,
differently.
the permissions are still foobarred.
Okay, hold on. Home works, and it is... Is this SE Linux?
It might be SE Linux. Let's disable it. Who needs SE Linux?
Oh, it actually logs everything. That's interesting. Hold on, let me just try running that again. Log up data.
How'd you fix Docker? That's a great...
Could have fixed Docker.
How do you fix Docker?
I think it's C Linux.
Yeah.
Oh, Zed. Let me try that. And so I probably need... Yes, that worked.
Hey,
SE Linux magic.
Now you should be able to run, gosh, what was it? Flow.tickle, tech design, and then the design. What's in designs? So if you ls the designs directory.
CI and SPM.
Okay. Yeah, so if you invoke flow.tickle with tac design and then SPM, it should run the entire flow.
Hold
I think
tickle.
it was tech design.
Tech. Wait. Spell it out.
Like hyphen design. Huh?
Okay.
There we go. And then SPM. I think that's, if I remember, I haven't touched this in a while.
I think that C does a chcon to like make it readable by the Docker daemon or something like that.
Yeah.
Or something like that. I don't know. PDK is not specified. So we have PDK root and we have /PDK. I'm also curious. I think I can unstmod my home directory now because I think that should be fine.
Specify
Yeah.
the PDK you're gonna run the
PDK or
God, what was it? You might be able to just export PDK to be Sky130A as an environment variable in here.
uppercase or
Yeah, uppercase A.
in the sky?
No, Sky's lowercase. That should be fine. We'll try that again.
That didn't work. The version of OpenPDK is just in building is...
It gets angry about this stuff.
Make PDK? No, it's already just gonna download everything.
So outside of the Docker container in the open lane directory, make PDK will download the PDK stuff. We already set that up though.
Oh, it's trying to use Docker and some virtual env stuff.
Yeah, open lane is kind of a wiggly mess.
It is downloading
what
it.
It's doing is it
grabbed Polari again, and then it's
it's acquiring the correct version of the.
Hey, that works.
We just grabbed the latest. Yeah. Okay, so what this is doing is it took the design files that were Verilog. Oh, right. Ignore mismatches.
Oh, that's ignore mismatches. Okay.
Yeah. So what now it's doing is doing all of the magic needed to actually do.
So what is it? Okay, so it did synthesis, single corner static timing analysis, initial floor planning, and it's complaining about the power grid. IO placement, tap D-tap insertion, power planning with power and ground, PD. I don't know what any of this is. Global placement, single corner static timing analysis, placement resizer design optimizations, detailed placement, single corner static timing analysis, clock tree synthesis, single corner static timing analysis, placement resizer time. You know, we need to get Cyan in here, and she can do like an ASMR of reading open like that, open lane output. It did have the same thing multiple times. Global routing.
Yeah, it's an incremental process.
Antenna repair, writing Verilog. More of the same. Fail insertion, wire length, SPEF extraction at the min process corner, multi-corner static timing analysis, SPEF extract. What's SPEF?
SPEF. I don't know. I don't remember.
Black box during SDA. Airdrop report. Magic. It runs magic.
Yes.
Left. GDS2. K-layout. So we also have K-layout in this container, I guess. So are the layouts using K-layout. Spice export. Powered Verilog. And writes Verilog again. LVS. Synopsis parasitics exchange format. Thank you.
Yes.
This is all really complicated.
It is a little complicated, yes.
Gadget DRC, LVS, open road antenna rule checker. Same current set of views. Flow complete.
Yep. And now it dropped all of the files in the designs SPM runs directory, so they're all there for you to investigate. And yeah, I'm familiar with PEX, parasitic extraction. I just didn't know the SPEF.
Okay, we have two, and one was the failed one, I guess. Cool.
Yeah.
It has all the logs and everything.
Yeah, so all of the final ASIC stuff would be in runs/final.
I think that was just the failed one, the previous one. So
results. Final, yeah, it's in final.
Cool.
Yep, and then you could open up the magic file and see what it synthesized.
Uh, 138 was broken. This is 138 though.
130 NB are, for all intents and purposes,
okay, I guess
interchangeable
130B.
when just looking at it.
Mag? SPM.mag?
Yep.
Whoa, that's a lot of stuff.
Yeah, but that took the code and it turned it into all of these wonderful gates.
That looks really complicated. Decap. Oh, is that decoupling capacitor?
Yeah, so it inserts
Cool.
decoupling capacitors and diodes and all that stuff.
So
And
there's like
these
a
are all
grid,
filler
right? It's like
instances.
power and ground is like a big
Yeah.
chunky power and ground, and then there's like less chunky, and then there's like less chunky.
Yeah,
Ah, that's really cool.
and then this, if I recall correctly, the place and route engine and the floor planning engine that OpenRoad uses is based on electrostatic simulation.
Ah,
It's actually quite cool. There's a paper on it, which I'll have to dig up to share. But
And
yeah.
I remember X. Cool. You can see them.
Yeah.
That's
you
really
can, You
cool.
can look into the cells.
So you can just like peek into.
Yeah.
Nice.
Yeah, so this is a hierarchical layout. There's also a way to flatten layouts, so what it gets rid of all of the cell references and collapses the geometry. But that makes larger layout files because
Right,
with
right.
hierarchical layouts, if you have lots of cells, they're instanced instead of
Right.
duplicated.
Otherwise, it's literally it makes sense.
Yeah.
Cool. So you can see like
Yeah.
all the silicon.
And these are all the standard cells.
Oh, and I can
that
I can
Yosef
show everything.
mapped.
I'm smart. I figure out how to show everything. That's really cool.
Yeah. Yeah, and so this is the result of Yosef taking the Verilog code, mapping it to the standard cells, and then the monstrosity that is OpenRoad and OpenLane chewing on the output format until you get an ASIC.
Nice.
And then it added pins all
I see
around
lots of
the
fillers
periphery,
and
so
stuff
this
there.
is-
Okay, so
Yeah,
so the
so there's a-
that's I think it's just power there on the side. I don't know where the pins are.
Oh, I know I'm hating on OpenLane a lot, but you all are doing great work. I understand how difficult the task is, but you know how it is with tools. Sometimes you just gotta hate on them to let out steam. It's not blaming the people behind it. I know y'all are working on it. You've done some great things
Oh, I
in the
see there,
last
okay.
2 years alone.
I found the pin.
Yeah, sorry, I'm responding to chat.
Yeah.
I don't want to make anyone feel bad because I'm not hating on anybody.
Oh, this is
And,
like
yeah,
a
it put
data
out-
bus?
Yeah.
Cool. Is this like a 32-bit something?
Yeah, if you go back into the OpenLane directory where the designs were, instead of going out to the runs, there should be
Okay,
a
so
Verilog file.
there's
which
a
has the
reset
design.
line, there's a 32-bit something. I'm just like guessing now. P
Yeah.
Y. I wonder what this is.
Yeah.
So where's what should I look at?
Yeah, so if you go up to Designs SPM, just in that directory,
Source?
in source, yep, the .v file is the logic. So OpenLane took this and turned it into the gates.
So we have clock, reset, X, Y, and P.
Yeah, I'm not
So it's
entirely
just-
sure what this is. I don't know if the comment on the top tells
So
us.
it's mostly inputs. The comment's just the license.
Oh, yeah.
And then I don't know what that T-comp CS had. Is this like a counter or something like that?
I don't know. I know it's just an example that I think it might just be a contrived example the OpenLane people use to test the flow.
It's a serial parallel multiplier.
Exciting.
I don't know what that is, but that sounds cool.
I liked all of the default designs that were shipped with older versions of OpenLane because you had things like there was a USB core and there was an AES core, and I think
Oh,
those all showed some pretty decent examples. But I can understand wanting to minimize it to one smaller example.
I still don't know what a serial parallel multiplier is.
Serial parallel multiplier. Yeah, I don't know. I don't actually know what that is.
Oh, is that like one operand is parallel and one operand is serial, and as you clock it, it's accumulating and giving you out. I think I get how this is going. And so you get 1 bit output per clock, and 1 bit input per clock of B, and 1 parallel bus of A? Am I on the right track here? Trying to think of how you would make a multiplier by adding repeatedly per clock. Cool, that's pretty awesome. Yeah, okay, now that makes sense now.
Yeah. Oh, so they're sub-modules now. I guess because I've never recursively cloned OpenLane.
Oh, okay, so I need to... Is it pull or fetch? Sync. No? I forgot how to get some modules work.
Yeah, that was just the CI submodule.
Update. That's what it was.
Yeah, that was just the CI module, not the extra designs.
There's a bunch of stuff here though. AES core, USB.
Oh no, I'm just stupid. Yeah, okay, they're all in CI. Yeah.
Cool.
Okay. I'm a dummy.
That's really nice.
Yeah, those are all examples that, as far as I know, place. Like, you've got, of course, your RISC-V core in there.
I'm kind of curious, like, how long does it take to compile a RISC-V like that? Like, can I just do it and see?
Yeah. I think you might...
Maybe that...
I don't remember how to... Maybe?
Looks like it.
Yeah, okay. I wasn't sure if that would work. This might take a minute. This is one of the smaller RISC-V cores too, the Pico RV32. It's a capable core, but it's one of the smaller ones.
Now I want to know if I dare open
RISC.
this in Magic and see an entire CPU. That might go over. I have a lot of RAM. I can say I have a lot of RAM, at least on this machine.
Yeah, but...
I'm glad I updated to this like Apple Silicon machine, because I'm sure this would be worse on the old Intel.
Yeah, I mean, it runs fine on my Threadripper. I think the average ASIC job for smaller ones, 10-ish minutes.
That's not bad.
Yeah. Risky command. 470 warnings. Warnings don't matter. Errors matter.
Mood.
The warnings are why we have silicon errata.
That's such a mood.
But yeah, your experience with Magic is why I'm writing my own tool.
I can understand that.
Yeah.
I mean, it's the kind you can kind of get used to it, but it's when
archaic.
it doesn't do what you want that it gets Yeah,
it's archaic. It's a tickle monstrosity. Yeah. It's powerful. I'll give it that. It's powerful. You can probably get really fast at it if you understand what makes it angry. Because the being able to type commands without actually having to do much, because you can do full navigation and everything via just commands. So you'll never need to touch the mouse if you get good enough. So I bet you can be pretty fast at it.
that's really cool that there's a Docker container with all this setup, though. Because I'm sure it would have been a lot more painful without. And also that it's available for ARM64. Thank you so much. Because
that's great.
I don't know.
I was half expecting needing to build this stuff.
So, tomorrow I have a collab with Cyan, and what we're doing is we're making the OBS browser work, because there is no ARM64 Flatpak of OBS, and the packages for Fedora don't have the real browser. So that's the kind of thing you have to do when you run on ARM64 and nobody has packaged the software you need for ARM64. So thank you for making it all easy like this.
Yeah, it's great. The people doing OpenLane and OpenRoad stuff, they're doing some great stuff. It is truly fantastic.
That's so cool.
Yeah. While this is running, if you want, there's some resources that the others might find, that chat might find interesting. There is something called SillyWiz, which is an in-browser editor, like Silicon Wizard.
SillyWiz, like one. Ah, tiny tape out.
Yeah. Tiny tapeout's another thing. So tiny tapeout is essentially an MPW running on top of an MPW.
Still going.
Yeah, SillyWiz is this in-browser tool that people can use to try what we just did with Magic. But
Oh, cool. And it's
simulation
literally like
stuff-
draw an in MOSFET and it tells you how to. Oh, that's really cool.
Yeah. I feel kind of bad because I explicitly wanted to do the trial by fire with you instead of going through something like this
No,
easily.
no. It's okay. It's okay.
But yeah, this is a good resource for people that want to get into it and learn this stuff.
So how do I
there's
launch?
also-
Can I launch it on the browser or?
Yeah.
Oh, here, appcitywiz.com.
app.sillywiz.
Oh, that's really cool. Okay, this is like fancy Web 2.0 stuff.
Yeah, and it does the simulation stuff, and
Nice. Oh, this is
that
really
should look
cool.
familiar. That's an
That's the same
inverter.
thing. Yeah, that's literally what we drew, right? Just with different dimensions.
Yeah.
Very different dimensions, but yes,
Yeah, very different dimensions, but it's still functionally identical.
nice.
Yep. And then there's Zero to ASIC, which is a course that Matt Venn offers, which is sort of a walkthrough project on fabricating an ASIC. I can shout out Matt Venn because he was a coworker of mine. It's pretty cool.
That's so cool.
Once upon a time, I worked at Yosis.
Ah,
But yeah, so there's a bunch of stuff. I believe this runs off of the paid eFabless shuttle. But if you want to invest a little money and get like a good community with it with other people, that's a good option.
that's really
That
cool.
tiny tape out is like this but smaller. So
That's really awesome.
yeah. Yeah, but there's definitely some resources getting put out there behind the open source silicon. This is a blossoming field.
I see detailed routing is taking a long time.
Oh yeah, you're routing an entire RISC-V CPU.
It's using more than one core.
Okay.
I'll give it. Wait, no, that's ARM core. It's using. That's just the screencast. Oh no. But no, OpenRoad is actually using more than one core, which is nice.
Yeah. The
And I
OpenRoad
see
tool's
it's
pretty
using
cool.
a. No, this one's not using that much RAM. I think it's probably browsers using all my RAM right now because of browsers.
Yeah, the OpenRoad is actually a tool where you can inspect the routing database to look at routing.
Oh, I finished
and
that one. Okay,
placement
now it's
congestion.
doing multi-corner static timing analysis.
Yeah. But yeah, introductory ASIC stuff. Now the world is at your fingertips. You're ready to design the next big thing.
Are we designing something?
I mean, we could be.
We may or may not have had some ideas.
Spoiler alert.
Spoiler alert. Ah,
But yeah, but this is a good step forward.
that was so much fun. I've never done that before. Like, I'd seen, like die shots and stuff on Google Images, but I never really knew how it worked. So that was awesome.
Yeah, and I think it's a lot less intimidating once you realize kind of what's going on and that some of these tools are actually generally accessible. Like, sure, the big industry is still going to use Cadence Virtuoso. I don't even know how expensive. It's got to be at least licensing in the millions of dollars.
I don't even want to know.
And then that's not counting the PDK NDAs and all the stuff you need to get access to, like the TSMC PDKs and stuff to load into it. It's just a huge nightmare. So that open source tools are available, and there's a way for people who are interested in this to get their designs actually made into something physical that works. It's like when PCB manufacturing became generally available, right?
Because now everyone can just make widgets. On what was that website? I think it was like this. Is it a Hong Kong company that was doing it? I forget. It was like Seed Studio and some other one, I think. But yeah, that stuff.
Yeah,
right?
Seed Studio.
What's the other one? The distributor.
Oh gosh, I don't know. Adafruit's another one. They do boards and.
I mean, like there was like that one distributor in China that also did manufacture now, and I forgot who it was.
PCBWay.
No.
Oh, they just do PCBs. I'm not entirely sure who you're talking about. Yeah, but it.
Oshpark is one, but I wasn't thinking of Oshpark. I was thinking of the. What was it? I forgot. They're like DigiKey, but in China, and then they also do JLC PCB. That was. No, but it was yet another one. LCSC, yeah, LCSC is what I was thinking of. I think they also do like
LCSC.
Yeah.
JLC PCB is owned by LCSC.
Yeah.
So they're both owned by the same parent company.
And like these days, you can just make your own design with their stock and like have them make it, right? Which is really cool.
Yeah, especially if you use I don't like it. I think it's a terrible piece of software, but their Easy EDA software. It's like a web-based PCB and
Max Fine-out violations. Okay, we have warnings. Do we dare open this in Magic?
If you want pain.
Design CI risk ICO-RV runs.
Results final.
Mag. Let's see. Let's get pain. Pain time. That's a big chip. That didn't even take that long.
Yeah, and you can see how it's just kind of like a logic blob.
That's crazy.
But it's an absolutely huge chip.
It takes time to just draw the labels, right? It's just that's the text, right? That is like taking forever to draw.
Yeah.
I like that you can see the general shape of the blob.
Yeah. It's just blob of logic.
That's so cool.
Yeah.
So I can X a bunch of this and see the cells. How much can I X before everything goes wrong?
I don't know.
See, that's a pretty good. Oh, let's just try it. Wow! Actually, that isn't that bad considering what it's drawing. It's drawing every single thing in every single box in the layout for an entire CPU. That's actually kind of impressive.
Yep.
I was expecting it to be very angry at me if I tried this. And I think it's even the font rendering that I was having so much trouble with.
Yeah, Magic's been around for long enough. It's fairly robust. It's still not the best thing ever.
That's pretty impressive.
Yeah. But yeah, there you go. There's your very own synthesized RISC 532-bit core.
That's so cool!
Yeah.
Awesome!
Yeah. So I think that was a pretty good introduction.
Yeah. Thank you so much. I had a lot of fun.
Yeah, anytime.
I feel like I'm just gonna stare at this for like the next 2 hours.
Yeah. You can plot these to like SVGs and stuff, and yeah, there's a whole way to turn them into 3D models by taking the GDS2 files and exporting them into step files and then importing those into Blender, and yeah.
That's awesome. Yeah, that's how you did the. So on the thumbnail, right? Aki gave me that 3D render that we used, and that was also a buffer, right?
Yes, that was the standard cell buffer from Sky 130B.
That's so cool.
Yeah.
All right, should we call it? Actually, why don't give me? I'm gonna take a quick break for a minute, and then maybe we can take some questions or just chat a bit before ending the stream.
Yeah, that works for me.
All right, give me a second. Let me see if I can figure out how to make you be around. No, that's not the right button. Where's the button? Hold on.
Button.
OBS is hard.
Yeah. Sleepy beepy.
Okay, I'm gonna let you keep people entertained, and I'll be right back.
Oh no.
I'll be right back.
Yeah. Wah. Yeah, but I hope everyone enjoyed it, and I hope I didn't do a disservice to it. I'm not like an instructor or anything, so I tried my best. Hi. I have a terrible, like, 10-second delay with chat and stream. I apologize. Jackie, so funny you mentioned that. There's actually a project which is doing tech mapping between Verilog and 7400 series logic. So you can take Verilog and map it into something you could probably actually breadboard. Oh, exciting to hear that there'll be a PR to fix some of the annoyances. I don't honestly actually remember any of the annoyances. I have blocked them out. But I will be definitely keeping an eye out for that, because that sounds exciting. Yeah, maybe for another stream, if I can convince Lena, we can do some HDL shenanigans and synthesize it to 7400 series logic. I was actually writing a Yosis pass that did discrete transistor synthesis. So it would take it kind of like layout, but instead of mapping to standard cells, it would map to Verilog analogs that I designed, which are basically MOSFET gates, but then that's all flattened down into an individual transistorized layout, and then that's physically exported as a KiCad schematic and board file, which could then be manufactured. So it's kind of like the ASIC flow, but bigger. But yeah, I'll have to talk to Lena, but maybe we can put the notes. I have a big note file thing with what we did today, which mainly just goes through actually drawing the transistor. So maybe Lena can tweet that out or something to share it with everybody. The tool from the beginning which turned Verilog into a picture. If you're talking about the entire ASIC flow, that's OpenLane, and that's Yosis and a whole bunch of other tools that take the Verilog and map it to PDK standard cells. And then that is then laid out. And take Verilog and map it into logic sand. I wonder if you could do that. I know people have done taking VHDL and turning it into redstone for Minecraft. I know that's a thing people have done. Yeah, yeah. Wow, 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 wow. But yeah, I am happy you were all here. I am happy I did this with Lena, and hopefully there are some more shenanigans with this in the future that are a little more planned out. This was kind of an impromptu stream that I just threw some notes together. I was not ready. I am not a lecturer, so I apologize for any of the rough teachings and things I didn't know, but I am happy to admit that I don't know things when I don't know them. Which I hope is an admirable trait. Anyway, I'm getting off topic. I'm pretty sure someone already did Verilog to Redstone. I know they did VHDL to Redstone. I'm pretty sure they did Verilog to Redstone. Oh, thank you all. That means a lot. I kind of have to flex my HDL chops and my EDA chops a little bit after working for Yosis, so you know.
I'm back.
Hi, welcome back.
It's just back to the screen. There.
Yeah.
So I actually have a bit of a story because the why I realized what the serial parallel multiplier was. So I actually took a digital logic class once. That was a while ago, and one of the like homework that we had was make a serial adder, like a serial adder with carry. So 2 bits input, 1 bit output, and so I was just like, okay, well, you know, I'll just make a full adder and then have a register for the carry, and that's it, right? That's the entire thing. And so I submitted that, and the teacher was like, no, but you have to do like the Karnaugh maps and all this other stuff, and I'm like, but it's just a serial adder. Why are you gonna make everything so complicated? And so I recognize that this is like the multiplier version of that, right? It's just accumulating multiple bits every time. So I was just like, oh, I think I know that serial thing.
Yeah. I am not formally trained in any logic. I learned this all off the cuff, so there's
to be clear, this was a very
introductory
class and like nothing that is actually useful, I think, for any of this. So I still don't know what I'm doing, but it was a course that I did take once.
Yeah, well, do any of us know what we're really doing? Because I sure as heck don't. Yeah.
Oh, it's complaining about the beep versus A thing, but I guess it works anyway. Thank you so much for checking OpenLane and Volar out. By the way, I'm still gonna start it. What? No, thank you for making these awesome tools.
Yeah, they're great. I can't sing enough praise for the open source silicon and EDA tooling in general.
It's really crazy that you can do this at all with open source, like the end to end, right? And you submit it and get a chip made.
Yeah, basically it's almost entirely end to end, unless you want to start manufacturing the photomasks and
yeah, but I mean,
etching yourself.
That's a mission, right? You know, up to all the way to the fab.
Yeah, and the fact that multi-project wafers and this stuff is generally more accessible to the public in the first place is great. Because multi-project wafers only used to be university stuff, if I recall.
Right. Because I think I remember that when I first heard news about this stuff, it was like, like, oh, if in this university you can make chips and stuff. But now anyone can do it, right?
Yeah, and there's a few other multi-project wafer things going out there. I don't remember the name of it. A friend showed it to me, but they have you have to sign NDAs. And it's not entirely open source, but it lets you use the TSMC. It's in the 2-digit nanometer PDK.
Oh, that's pretty cool.
Yeah. Granted, it still wants like Virtuoso and the proprietary tools, but the fact that that's even an option at all is kind of great.
That's so cool.
Yeah. So I guess we can do questions, comments, concerns,
Yeah.
fears, quandaries if you want.
Let us know if you have any questions or what you want to talk about.
Yeah. Yeah. This chat delay is pretty rough.
I have the delay set to like medium, so it shouldn't be that bad. But the thing is, YouTube has a bad habit of, it's not like Twitch, which is always real time, right? YouTube will just let you go back in time, but it will also lag randomly. And unless you manually notice and catch it up, it just gets worse and worse depending on what happens. So it's kind of annoying for viewers because they have to keep like clicking the live button if it just lags.
Yeah. Let's see. Any other types of course that could be taken on subjects related to this? Digital logic courses are pretty good. There's a lot of open, like MIT OpenCourseWare has some pretty good stuff. And also, I will have to find a link if it would be okay to share this in chat, Lena. There's a professor on YouTube that does...
Send it to me on Discord and I'll post it in chat because I think it's not going to let you post the link, but it should let me post the link.
It's this professor and he does a lot of digital logic stuff, and he actually did some hierarchical tutorials for magic and layout and stuff.
Awesome. Let's see if I can...
I semi-lifted the thing from him.
Okay, I don't know, am I the only person who gets this? Like, YouTube has this hard button on the right of the chat, and it just like perfectly overlays the menu for the last chat message, so you can't use it. And I like, this has been broken for like forever. Am I the only one that, like, I don't get?
No, I have that problem too.
I don't get it. Anyway, hopefully the message arrived. I pinned it. I think that worked.
Yeah. He does some great videos. He does a lot of CMOS transistor logic stuff, and he does some. He did some Sky 130 and open source stuff too. So definitely good videos if you're more of a lecture learner, because he does a lot of whiteboard stuff and all that stuff. So it's pretty good. And there's a bunch of resources out there that if you're interested in, you can definitely find. So.
Here you go. That's so cool. I'm glad the link worked.
Yeah.
When's the trial of fire going to begin?
We already did the trial by fire.
Yeah.
Let's see, what else is there? Is this thing in Magic Program self-drawn? What's currently on screen was done by OpenLane. It's part of a RISC-V core. Yeah, anything involving magic is trial by fire. Oh gosh, yeah, it's so true. I hate this application with a burning passion. Yeah, it's just K-layout is not capable enough to replace magic, and it's also not as easy to use. So again, I'm trying to write my own stuff.
How can you test your chip designed like that without production? So you can simulate it to some extent, right?
Yeah, so you can do a full gate level simulation where you actually take all of this geometry and do a physical simulation of it, but that takes weeks.
That's crazy.
And that's if you want like a physical simulation. For logical simulation, which is what you tend to do before, your HDL has test benches to make sure it functions properly. And then you really only move to design and tape out of the ASIC once all your local test benches and logic design tests pass. There are some edge cases where you need to do gate level simulation, not necessarily like physical simulation of all the electrical signals, but like gate level logic simulation. There's a few expensive things out there for it. There's the Protium and Palladium systems from Cadence.
You have something like that, right? The one thing you got for cheap?
Yeah, I have a HAPS 80D, which has a single giant Xilinx FPGA in it. But what it does is essentially converts it to a gate level simulation, and it runs it on an FPGA. And for larger ASICs, you need much bigger systems.
Mm-hmm. But for something that you would do for one of the Skywater, like Caravel harness thing, I imagine for the most part you can fit that kind of stuff inside a big FPGA.
You could probably fit a full Caravel tape out inside a large FPGA, yeah.
Mm-hmm.
It would have to be a large FPGA though.
Mm-hmm. And I guess it will also run slower than the real thing.
Yeah, gate level simulation, as far as I know, even for like the fastest simulation designs, never top out over 100 megahertz of simulated speed. You could probably get faster than that if you do some really specific stuff, but if you're simulating a full ASIC or like a GPU or something, you're gonna get maybe tens of megahertz.
Can we compile it to Game of Life? Probably. I'm kind of guessing you could probably use this flow to make a Game of Life design.
Yeah, probably.
I guess I don't see why not, if it's just polygons anyway. It'd be really silly, but I guess you could do it. If you have the standard cells, which I'm pretty sure people have made all the basic logic cells in Game of Life already.
Late to the stream, what's the usage of this ASIC? The stream was just an introductory course to VLSI layout and stuff. This particular ASIC is a RISC-V core.
And it's really
Not
big.
a chunky one. This is one of the smaller cores though, too. I mean, it's not a bit serial RISC-V, but it's a smaller core. Yeah. The fact this is possible at all is honestly kind of fantastic.
Yeah. It's
Got an
really
open source
crazy.
processor turned into silicon with open source tools. Slowly getting to the dream of a full open source ecosystem.
Yeah. No specific use, but what could be useful. It's a CPU, right? So,
Yeah.
it's you'd have to put it into something, to make it useful. But it's this one's just a demo, right? It's like a test, for the software. But if you put it into, I assume this one also has I/O. I haven't looked at the edge. Yeah. Like, it has all the pins, right? So it's a CPU. You could hook it up to something else, and then it would it would be a CPU.
No, this is not the 64-bit. It's the Pico RV32, which is one of the smaller 32-bit minimal RISC-V cores. So it doesn't have like the atomics or any of the really fancy stuff. But yeah, lots of fun stuff. And then what you can do too is you can synthesize these big blocks, right? And they're called macro blocks. So this would be like a Pico RV32 macro block. And then what you can do is you only have to synthesize it and lay it out once.
Right, and then you just copy and paste it basically right into some other...
Yeah, and then you can include it in other designs, and then the floor planning stuff will place the big blocks and then connect them.
And that's how all the commercial socks are made, right? If you...
Yeah, it's called hardening, is what they call it. You harden your cells into a macro. So, like, the CPU cache would be probably an SRAM macro.
Yeah, so like you can see that there's like the CPU cores, of course, they only lay them out once, and then they mirror them, which is interesting. So they're like, because I guess you can take a hard macro and flip it in any direction, right?
Yeah, you should be able to flip it.
So they have like the CPU cores, and like they only laid this out once, and then they just instantiated it 8 times for all the cores. And the same with the E cores, they just lay out once and then instantiate it. And all the GPU cores, you know, they only laid this out once, but then inside also they will have like these squares, which I'm guessing is SRAM, and each one would only be done once, and then they would
and it's all hierarchical too.
And also this stuff,
So
like the cache, it will be like, you can see it's mirrored, right? So they only did this like corner and then mirrored it here and then mirrored it down here and here. So
yeah. And then the cool part with the hierarchical layout is because it's all instances, if you notice a small issue in one of the sub-instances, you only have to fix it in one place, and it gets reflected across all of the other instances. The problem is tape out is expensive and it takes a long time, so you don't want any mistakes.
You know, the reason why the previous stream, the performance counters, Apple actually censors those in production releases, but they forgot the A0 like first tape out like version uncensored on some iOS version, and that's why we have it. It was literally A0 and then the production one, and the EA0 was the one that they just forgot about.
Yeah. To answer MM questions, doing something like stacked dies, you can't do it on the Skywater process. That's a more advanced process. That involves things like through silicon vias, and you have to do back grinding of the wafers, and it just is exponentially more expensive. So for the simple stuff that the open source stuff is targeting, not necessarily, but you could design something for that, right?
And you could definitely do like the package on package stuff, right? In principle, right? Like if you have the WLCSP and you somehow get someone to package the routing to put RAM on top, I don't see why you couldn't do it. Because for those, it's just the regular die, right? It's not anything weird.
Yeah, you'd still have to do back grinding and a whole bunch of other stuff. Package on package is kind of complicated.
Yeah, but that's a packaging problem, right? It's not a silicon design problem. So the silicon design for that one, yeah, the silicon design should be mostly the same, but the actual packaging that's a packaging technology thing.
It looks like there are empty spaces on the efficiency cores. Why is that? It's mainly density, cell density.
No, like I think it's just confusing. So this is cache. Oh, the grid here is cache. And when you see little grid things, it's pretty much always RAM. And then this other thing that looks like empty space, that's actually the standard cells. So the like light areas here are actually the logic.
Yeah.
And then the little squares are the RAM.
Yeah. And those would be the register. I don't know if the register files would be done that way, but definitely the caches would probably be built using.
Oh yeah, the cache is like this is the L2 cache for the efficiency cores, right? And here for the performance cores.
Yeah.
No, those are the really obvious ones.
Yeah, and there's special software like there's OpenRAM, which is one that's used in the Skywater PDK stuff. It's a memory compiler where you give it a configuration of how you want your memory to look, like how many rows, how many columns, how wide is it, how many read ports, how many write ports, and then it generates a giant block of SRAM for you, because doing it manually is just a slog. And yeah, they're called memory compilers. But yeah,
and you can also
once
see
you
like there's
kinda
like
know what's going on-
rectangles, right? So they probably laid these sub blocks out separately and then
Yeah, maybe.
instantiated them.
It's hard to tell without like more resolution, but this is what process node is this? It's very small.
Oh, this is like 5 nanometers or something, I think.
Yeah, 5 nanometer. It's super small, so it's hard to without being able to kind of see
5 nanometers. So
how the gates are laid out and do kind of comparisons that way, or seeing the actual layout. It's difficult to tell, but it's very likely that these macro blocks are made of sub macro blocks and so on, just because it makes designing easier. And then yeah, the LPDDR5 interfaces are probably bought out by Synopsys, maybe?
yeah, I think the memory is Synopsys.
It wouldn't surprise me. They do a lot of IP for memory and interface stuff. But yeah.
It'd be
Another
really
cool
cool
thing
if
they
we
could
get.
do,
Oh,
too.
sorry. Go ahead.
Oh no, I was gonna say it would be cool. What they could probably do is have the performance cores as a procedural macro block. So it would have a 2x2, and then you could say, okay, but we actually want this to be 4x4, whatever, and it could do that procedurally because it seems to be fairly identical.
But yeah, no, like I mean, these are obviously. That's a single core, right? So they only laid that out once, but then I don't know how they do the actual routing when they have more than one.
Yeah, it's probably on extra metal layers. So all the local stuff would be on local interconnects and the first metal layer and the second metal layer, and then I don't know how many metal layers the 5 nanometer TSMC process has.
It's
All of
probably
that
like
stuff's
15
under,
or something.
Yeah, it's under super secret NDA stuff.
Oh, I know. It says it's more than 10 UV layers. And then all the
10 UV layers, but that's... Oh god, are they doing double patterning?
I have no idea. Okay, that's the number of masks.
The number of masks is normally the number of layers you get.
I think you can probably find someone that counted the layers.
Yeah. It's probably quite a few layers. I think I've seen some talk of PDKs with, it was something like 20 metal layers or something. But yeah, it gets dense very quickly.
N5 process is UV on up to 14 layers, but then there's going to be more layers on top of that, so yeah.
Yeah, because the EUV machines are big and slow, so you want to minimize the number of layers you actually need to pattern on those. Which is why, actually, I have... something that you could probably show, which shows the Sky 130 stack up.
Ah! Yeah, let's
It's not
do
to
that.
scale, of course, but it kind of shows
Oh, that's really
how...
cool. Oh, so it's 5 layers.
Yeah,
Okay,
and it
that's
kinda-
nice and simple.
Yeah, but as you see, the layers get thicker and bigger as you go up because it takes more time to do fine-pitched layers. And for throughput reasons, you really want to minimize the number of very high resolution and fine pitches you need.
So this is what we had, right? The local interconnect, the local, like the connectors, the contacts, the poly gates, field. That's cool.
Yeah, and then we can also do capacitors too, like the upper.
Yeah, I saw
two
these.
metal
So they
layers.
actually stick capacitors on the bottom? Like in between
yeah, and then you
layers?
can stack capacitors to get larger capacitance.
That's really
and then
cool.
You can also do resistors. I think field poly does the resistance. So you get your sheet resistance, and yeah.
That's
And
really
of course,
cool.
it's not to scale, but yeah, that's generally the stack up for the Skywater 130 process. Which
So
is kind of
cool.
why you'll experience it too, and if you don't know that this is how it's layered up, it's kind of mysterious. The design rules get larger the higher up the stack you go. because the features are so much larger. And if you didn't know that, oh, that's because, you know, things are getting bigger, then you'd be like, well, why can't I put them this close on this layer?
Mm-hmm. That's so cool. So if you know what would be really cool is if we can actually design something and get it made
Yeah,
on
that
the
would be
MPW.
really exciting.
And then we could like take a photo of it like with a microscope or something.
Yeah, that would be a very fun project. Get the nullptr live logo etched in silicon
Yeah.
for all eternity. First VTuber group to do that.
Yes, we should do that.
Yeah.
Wait,
But,
Sky 130 also has resistive RAM between metal one. Wait, like resistive RAM? Really?
Yeah, I'm not sure about that. I don't personally remember reading anything about that, but I have not read too much up on the differences between A and B. I know a lot of people say, oh, you should have to use A, but...
It's... Huh.
Oh yeah, ReRAM.
What is that? Is that like... I've never heard of this before.
Yeah, neither have I. This is actually something new. It is a novel RAM technology.
So is it
Oh, okay.
like persistent or...
This is neat. I'll have
Is
to
it-
read up on this.
Is this non-volatile or is it... Huh.
That's
That's
one of the
so
benefits
cool.
of having these open PDKs is
Uh-huh.
a lot of research can be done for novel things like this.
I wonder if we can use this on the MPWs.
Maybe.
It says 130.
I know Google is working with Skywater to release their 90 nanometer PDK,
Mm.
which is exciting. And then Google also teamed up with Global Foundries for their 180 nanometer PDK. So
That's so cool.
yeah,
Wonder if you could use this on the... with Caravel.
maybe.
Cloudflare, why you gotta be Cloudflare? GitLab wants me to sign in to see that. Okay. We'll skip that.
We can do it later.
That's so cool though. Oh, so it goes between middle 1 and 2, and then there's literally just a thing there. Huh.
I guess that's more compact than SRAM, which I can see
Yeah, because
why it would
it's-
be.
It's just one link, right? So, because SRAM you need like 4 transistors or something.
Yeah.
Huh.
Oh, I didn't realize that the wafer's done for A and B. I thought it was they moved on to one or the other. Today I learned.
Oh, wait,
And,
do
yeah,
they
the
do
PDK
both?
is. Yeah, according to Muhammad.
Cool.
Hey, you wouldn't happen to be hiring at eFabless, would you? I need a job. But yeah, in all seriousness, that's pretty cool. There's the documentation does need a lot of work, but I figure as people are going to get into it, it's going to improve.
That's so cool.
But yeah, I can see how that's more compact than SRAM.
And it's non-volatile, right? Which is really awesome.
Yeah, I slightly worry about the speed, but I guess it'd have to be, you know, simulated to see. Because that'd be really cool for a novel FPGA architecture.
I was
being able to
thinking that you
stick
could use
the-
it like to replace a flash, right? Like to have a ROM that you program once and then it should be pretty
Yeah,
fast to
maybe.
read.
Yeah, I was thinking of replacing the SRAM cells in
Mhm.
FPGA LUTs for configuration, because then you could stick it directly over the multiplexers and save a lot of
Mhm.
area.
Is there like a general overview of how this works? Yeah, it's non-volatile. So it's memristor stuff. Okay, I've heard about that.
Oh god, memristors. Those were a thing in the TTL days, I believe, as well. sharp.
Huh.
Oh wow, ReRAM is old.
Yeah. 2000s.
Today I learned. And yeah, when you're getting into the CMOS layout and ASICs, chemistry and physics come hand in hand.
I wonder what the like write times are.
Yeah, that's a good question. Like, if it's comparable to SRAM, that'd be.
Oh, this
pretty
is 10
interesting for
nanoseconds. That's pretty cool. 10 nanoseconds
Yeah, but I
is
wonder
like
if that 10 nanoseconds is at the smaller 30 nanometer scale.
Mhm.
Very cool.
I kind of want to try using this now.
Yeah. Well, I mean, you can always make a design with it.
Ah,
You'll probably have to manually build the PDK with it. So
like with this stuff, yeah.
yeah. But yeah, this actually shows you a good example of how the PDK stuff is set up.
Oh, like so they tested, right? There's the like the memristor and the transistor and the spice.
Yeah. Yeah, I think that's X-Schem that is shown there.
That's cool.
Yeah. I mean, saving space on a chip is great because SRAM has trouble shrinking. And at some point, you just can't shrink the SRAM cells.
And I mean, if it's
Which is
non-volatile, I wonder what the like cycle endurance is.
Yeah, I'm not entirely sure what the cycle endurance is. IEEE. Those, you're gonna want to
Yeah.
excite those.
Yeah. Oh, this actually has the doxer.
Oh, that's a breath of fresh air.
It's actually 500k cycles.
That's not too bad.
So you wouldn't want to use it to replace RAM because you'd run out of cycles really quickly if you were using it as regular RAM. But for any kind of non-volatile storage, that's really nice.
Yeah. Yeah, that's a good question about how it compares in power usage.
Yeah.
Because it is a resistor, right? So. Oh yeah, this one wants you to.
Yeah, that one does, yeah.
Sign in. Boo. But yeah, any other questions, I guess, before we wrap up? Because I think we've been going for almost 4 hours.
Yep, 3 hours, 58 minutes. Probably a good time to stop. Anything else? Any other questions? Anything else you want to say?
I just want to thank everybody for being here. It's great so many people were interested in the trash fire this one. No, it wasn't that bad. I thank you. Lena, you did great.
Thank you. That was super interesting. Like, I want to make a trip now.
Yeah, I think that's definitely something that'll be fun that we could do.
Wonder what we should make.
Yeah, we should. Well, we'll have to talk to Luna and the others and see what they want to join into. If not, we can still do it ourselves.
Oh, Let's see if I can try running this on old Core 2 machine. Honestly, I don't know what the memory usage is like, but I don't think it's going to be unusable on older machines. So you might just have to wait, 10 minutes or 15 instead of 5.
Yeah, it'll just take a while. When is magic going to be actually magic? Magic's already actually magic. The fact it doesn't crash as often as it should.
Yeah. Also, I wasn't using more than like 2 cores, I think, when I was doing the slow stuff. So, I don't think it would, downscale badly to fewer core machines than the one I have.
Yeah.
So it should be fine. I'm actually pretty impressed by how fast it runs here. Considering you're doing we just did a full layout of a RISC-V.
Yeah. Well, we'll see how that holds up doing a full chip layout of a full 10 square millimeters.
Yeah. How big is that?
That's
in
a lot.
terms like this, how big is this in compared to the Caravel? What can I see the
Small.
dimensions here? I guess I can.
If you select it with a box
Yeah.
and then hit the B key, it'll print it in the terminal.
Okay, so this is microns 500. Okay, so half a millimeter by half a millimeter.
Yeah, half millimeter by half millimeter, just about.
And how much do we get on Caravel?
10 millimeters squared.
And this is 1/4 of millimeter squared. So it would be 40 times more.
Yeah, I think so.
That's not crazy. Especially
No, it's a
especially
lot.
if we can do the like doing it in modules, right? The like macros or whatever we call that.
Yeah.
That sounds doable.
Yeah, you'll get better cell density if you merge everything together, but you get better modularity and reproducibility if you do hardened macros. So it's
Yeah,
just
of
a
course.
trade-off, right?
That makes sense.
But yeah, but 10 millimeters squared when we're running effectively 150 nanometer process, it's loads of space.
We need to build something.
Yeah, I agree.
All right. I guess time to end the stream. Anything else? Any other comments from the chat? If not, I think we'll be calling it a day. Thank you everyone for coming. Thank you so much. We had folks like Mohammed that did actually work on this stuff. I had no idea that we were gonna get that. So that's really awesome. Thank you so much. Thank you to everyone who worked on the PDKs and the tooling, and I can remember all the pieces that are involved in what we did, but it's pretty awesome. And yeah, let's see if we can build something with this. I think we should make this a bit of a what's the word I'm looking for?
A series?
Yeah, series. Yes.
Yeah, I look forward to that. That could be a lot of fun.
All right, everyone. In that case, I think we'll be calling it a day. I need to get some food. It's a bit late. And you probably... I don't know what your sleep schedule is like, but I'm pretty sure it's late where you are right now.
Yeah, it's about midnight.
Yeah, all right. So, yeah, thank you, everyone. I'll see you next time. Hopefully we'll make a... I don't know. Oh, yeah. Collab with Sam tomorrow. We're going to be packaging OBS browser. And it's going to be really cursed. And yeah, a pain. So if you want to see me hate myself trying to package OBS browser and compiling Ceph, joining tomorrow. It's a couple hours before the start time today. And every time I screw up and I have to recompile, it's going to be 48 minutes. So depending on how many times I screw up, we might have a lot of random chat time. So I'm hoping not. But yeah, that's our little plan for tomorrow. And for those who have joined in for the first time, my regular streams are on Wednesday and Friday at the same time as this one. Again, in Japan at 1 p.m. Japan time, and I usually work on the open source GPU drivers for the M1. So yeah, and look forward to more streams about ASICs, because now I really want to start building something. So, right, we're gonna make something, right?
Yeah, we're absolutely gonna make something.
All right, so thank you, everyone. We'll see you all next time. Bye bye.